This is a space where you can let your day slowly fall away, where curiosity becomes a companion to rest, and where science drifts softly in the background like a lullaby for the mind. Tonight, we're turning to one of the most intriguing and puzzling ideas in all of science and philosophy, the possibility that consciousness itself might be linked to the strange world of quantum physics. Before we begin, I'd love to know where in the world you're listening from. People tune in from every corner of the globe, and it's always fascinating to see the little constellation of viewers who gather here each night. If you're enjoying these quiet explorations, a gentle reminder to like the video and subscribe. And to those of you who are already subscribed, thank you so much for supporting this channel and helping it grow. And one more thing, if you'd like to explore the world a little closer to home, please check out our new channel, The Sleepy Geographer. You'll find the link waiting in the video description. Now, I hope this video isn't so fascinating that it keeps you wide awake until morning. But if the ideas happen to hold your attention longer than planned, at least you'll drift away having learned something wonderfully strange about the universe. So let's settle in, breathe slowly, and let the mind wander. Because here is the question: could the secrets of our own awareness be hidden in the quantum fabric of reality itself? Consciousness is one of those things that everyone experiences intimately, but no one can quite explain. You wake each day into a world of thoughts, memories and sensations, yet when scientists peer into the brain, what they see are firing neurons, chemical messengers, and electrical patterns. The leap from those physical processes to the experience of being you, with all the colours, emotions and ideas that swirl in the mind, is what many call the hard problem of consciousness. At the same time, quantum physics stands as one of the most successful yet bewildering theories in science. It describes the tiny building blocks of matter not as solid little marbles, but as clouds of probabilities, particles that can be in two places at once, entangled across space, and influenced by the mere act of measurement. Quantum mechanics explains lasers, computers, and even the chemistry of life itself, but it also leaves us with puzzles about what reality actually is. It is perhaps no surprise then that some have wondered whether these two great mysteries, the enigma of the mind and the strangeness of the quantum world, might somehow be connected. Could the unusual behaviour of particles be more than a curiosity of physics? Could it also hold the key to why we have inner lives, why we are aware, and why thoughts arise in the first place? Over the years, many thinkers, from respected physicists to speculative philosophers, have proposed ways that consciousness might emerge from quantum processes. Some have imagined that the brain works like a quantum computer, harnessing strange effects to give rise to creativity and awareness. Others have suggested that the act of observation itself, so central to quantum mechanics, requires a conscious mind, and that our awareness might play a role in shaping reality. But for every such suggestion, there has been skepticism. Most neuroscientists believe the brain can be fully explained by classical physics, with no need to reach into the quantum domain. They argue that the warm, noisy environment of a brain is the last place fragile quantum effects could survive. To them, linking consciousness to quantum mechanics is more poetry than science. This video is an attempt to walk carefully between both sides, to explore the allure of the idea without overstating it, to share the difficulties without dismissing the wonder. You'll hear about the history of the theory, the arguments for and against, the evidence we do and don't have, and the cultural fascination that has made this one of the most talked about, yet least proven ideas in science. So as you drift into this journey, keep in mind that whether consciousness turns out to be quantum or not, the mystery of awareness remains one of the most beautiful puzzles of all. Tonight, we will wander slowly through the physics, the philosophy, and the speculation, gently exploring the possibility that the essence of thought might be written in the language of the quantum world. Consciousness is both the most ordinary thing in the world and the most extraordinary. You wake up every morning, and there it is, ready to greet you. Thoughts appear, sensations flood in, memories drift to the surface. It feels obvious, almost effortless, to be aware. And yet, when scientists try to explain what awareness actually is, they quickly find themselves staring into one of the deepest puzzles in all of science. Philosopher David Chalmers coined the phrase the hard problem of consciousness in the 1990s to describe this enigma. The easy problems, as he put it, involve figuring out how the brain processes information, how neurons fire, how we react to stimuli, and how behavior arises. These questions are far from simple, but in principle, they seem solvable. Neuroscientists can map electrical activity, watch networks light up, and trace the pathways of signals. But the hard problem is something altogether different. How do all those physical processes translate into the inner world of experience? Why is it that when light waves strike your eyes and trigger electrical signals, you don't just behave like a machine responding to input? You also see the brilliant red of a sunset or feel the sting of a paper cut. This distinction is at the heart of the puzzle. On one hand, the brain is a physical organ. It is made of neurons which communicate with each other using electrical impulses and chemical messengers called neurotransmitters. We can record these signals, model them, and even predict how a person might move or react. But on the other hand, there is the subjective side, the taste of your favourite food, the feeling of warmth on your skin, the way a song can make you nostalgic. That inner first-person perspective is what philosophers call qualia, the raw building blocks of experience. And here's where the mystery sharpens. If you were to open a brain and examine it with the most advanced tools imaginable, you would find neurons and molecules, but you would not see the colour blue, or the sound of laughter, or the ache of longing. These things exist in the realm of subjective experience, not in the wiring diagram of the nervous system. In other words, brain activity can be measured, but the lived feeling of being conscious remains invisible to anyone but you. It is a bit like peering into a computer and seeing billions of transistors flipping on and off. You can analyse the circuitry, measure the voltages, and trace the flow of information, but that doesn't tell you what it is like to play a video game, to feel suspense in a story, or to be moved by a piece of music. There is a gap between the hardware and the experience that runs on it. Consciousness lives in that gap, and bridging it is what makes the hard problem so hard. To make the point clearer, imagine you are craving a square of chocolate. Neuroscience can tell us that certain brain regions related to reward and pleasure light up. Hormones like dopamine are released, and neural circuits reinforce the desire. But ask yourself, where exactly in the folds of grey matter is the craving itself stored? Is it tucked away like a chocolate bar in the back of a cupboard? It seems absurd because the craving isn't a physical object you can point to. It is a subjective feeling that arises from brain activity but isn't identical to it. Humour aside, this gap has led many to wonder whether consciousness requires more than just the mechanics of neurons. Some argue that if we keep studying the brain closely enough, we will eventually close the gap. Others suspect there may be something fundamentally new to discover, that subjective experience might involve principles beyond the familiar rules of biology and classical physics. For centuries, philosophers have wrestled with this issue. René Descartes, in the 17th century, famously declared, "I think, therefore I am." He argued that the mind and body were two distinct substances, one physical, one immaterial. Modern neuroscience, however, has largely abandoned dualism in favour of physical explanations. After all, we can see direct links between brain states and mental states. A change in brain chemistry can alter mood, a stroke can affect speech, and a dose of caffeine can make thoughts race. The evidence strongly suggests that consciousness depends on the physical brain. Yet even with these insights, the feeling of being aware still resists easy explanation. Why does electrical activity feel like something from the inside? Why isn't it just silent machinery whirring away? Some liken it to the difference between a map and the territory. The map can describe the lay of the land, but it will never capture the actual experience of walking through a forest, hearing leaves crunch underfoot, or smelling the damp earth after rain. This is why the hard problem is not simply a scientific puzzle, but also a philosophical one. It forces us to ask whether our current scientific methods are enough to capture the inner side of experience, or whether something new is required. Perhaps it is only a matter of time until neuroscience provides a full account, or perhaps consciousness will remain forever beyond the reach of brain scans and equations. The difficulty also makes consciousness one of the most captivating subjects to think about before sleep. As you rest, awareness itself slips in and out of focus. Dreams appear, carrying their own vivid experiences, even though your eyes are closed and your body is still. Then, in deep sleep, awareness may vanish almost completely, only to return again when you awaken. All of this arises from the brain, yet none of it feels mechanical. It feels personal, mysterious, and strangely fragile. This sense of mystery is what draws so many thinkers, scientists and philosophers to explore possible explanations. Consciousness might emerge from the known laws of physics, from the interactions of billions of neurons, or as some have speculated, it might connect to stranger aspects of reality, domains we're only beginning to understand. Whatever the case, it remains one of the greatest challenges of modern thought: how to explain not just how brains work, but why there is someone inside to witness the working at all. And until that question is fully answered, the experience of being conscious will remain both familiar and unfathomable, the everyday miracle that makes every other part of life possible. Quantum physics is often described as the strangest yet most successful theory in science. It is the framework that allows us to understand the tiniest building blocks of the universe: atoms, electrons, photons, and the interactions that make up everything around us. Despite its bizarre rules, it has been tested to extraordinary precision. Without it, there would be no computers, no lasers, no smartphones, and no MRI machines. Yet for all its practical triumphs, quantum physics still feels more like a dream than a description of reality. One of the first peculiarities is superposition. In everyday life, objects are in one place at a time. A chair is either here or there, never both. But at the quantum scale, particles do not seem to follow such strict rules. An electron, for example, can exist in a superposition of states. In a way, it is both here and there until it is measured. A famous thought experiment often used to illustrate this is Schrödinger's cat, imagined by the Austrian physicist Erwin Schrödinger in the 1930s. In his scenario, a cat inside a sealed box could be linked to a quantum event, such as the decay of a radioactive atom. Because the atom is in a superposition of decayed and not decayed, the cat is imagined as being both alive and dead until the box is opened. While no one believes cats actually behave this way, the story captures just how odd superposition is. Next comes entanglement, a phenomenon Albert Einstein once dismissed as spooky action at a distance. When two particles interact in a certain way, they can become entangled, meaning their states are linked. Change the state of one particle, and the other responds instantly no matter how far apart they are. It is as though they share a secret code across the universe. Einstein doubted this could be real, but countless experiments have confirmed entanglement again and again. In fact, this phenomenon is now the basis for new technologies such as quantum cryptography and the early stages of quantum computing. Then there is uncertainty, captured in Werner Heisenberg's uncertainty principle. This principle does not mean scientists are sloppy with their measurements. Instead, it is built into the fabric of reality itself. For certain pairs of properties such as a particle's position and momentum, there is a fundamental limit to how precisely they can be known at the same time. The more carefully you pin down where a particle is, the less you can know about how fast it is moving, and vice versa. This is not a problem with equipment, but a natural feature of the quantum world. These three features, superposition, entanglement, and uncertainty, make quantum mechanics feel very different from the comforting laws of classical physics. In classical physics, if you know where something is and how fast it's moving, you can calculate its future with precision. Planets orbit predictably, pendulums swing steadily, and billiard balls collide exactly as expected. In quantum mechanics, certainty is replaced with probability. Instead of exact predictions, you get likelihoods and wave functions. Nature at its most fundamental level appears to shimmer with possibilities until a measurement is made. It is this shimmering quality that tempts people to link quantum physics with consciousness. After all, the mind itself feels elusive. Thoughts seem to appear and vanish. Awareness flickers in and out of focus, and free will feels slippery to define. If particles can be both here and there, might thoughts also inhabit more than one state before settling? If entanglement can connect particles across vast distances, could minds be connected in ways we do not yet understand? And if uncertainty limits knowledge, might that explain why consciousness feels so resistant to measurement? Such comparisons are not scientific evidence, but they reveal why the human imagination so easily weaves quantum ideas into the story of the mind. Superposition, for instance, resonates with the feeling of holding multiple possibilities in thought, like weighing two decisions before choosing one. Entanglement feels similar to the strange synchrony humans sometimes describe between close friends or loved ones. And uncertainty, with its refusal to give us exact answers, feels familiar to anyone who has ever wrestled with the ambiguity of feelings or the unpredictability of memory. Of course, scientists must be careful. The parallels can be poetic, but poetry is not proof. The brain is an organ made of cells and molecules, and there is no direct evidence yet that it uses quantum mechanics in the way a particle in a lab experiment does. But it is easy to see why the connection is alluring. Both consciousness and quantum physics share a reputation for being mysterious, puzzling, and strangely resistant to complete explanation. Both invite metaphors and both inspire debates that blend science, philosophy, and even a touch of wonder. Quantum physics, explained slowly and gently, is not really mystical. It is a rigorous mathematical framework that makes astonishingly accurate predictions. Yet when you pause and reflect on its principles, it is hard not to feel a sense of strangeness. A particle can exist in overlapping possibilities. Two particles can behave as one across unimaginable distances. And there are limits built into the very act of knowing. These are not everyday experiences, yet they are woven into the reality that underlies everything you see, feel, and think. Perhaps this is why, for some, quantum physics feels like the perfect partner to the puzzle of consciousness. If there is anywhere left in science where something profoundly new might be waiting to be discovered, it is here, in the intersection of the mind and the quantum world. And whether that link turns out to be real or not, simply entertaining the idea can be enough to spark wonder, curiosity, and a gentle reminder that reality is stranger and more beautiful than it first appears. In the early decades of the 20th century, as quantum mechanics was being developed, physicists were stunned by what their equations seemed to imply. Tiny particles, which should have behaved like miniature billiard balls, instead acted like waves of possibility. When measured, these waves seemed to collapse into definite outcomes. The mystery was simple to state but difficult to explain. Why did measurement make such a difference? What counted as a measurement? And more provocatively, did the conscious observer play a fundamental role in shaping reality? This puzzle became known as the measurement problem, and it gave rise to some of the earlier speculations linking consciousness with quantum physics. The Hungarian-American physicist John von Neumann, one of the great mathematical minds of the 20th century, was among the first to articulate the idea. In his 1932 book Mathematical Foundations of Quantum Mechanics, von Neumann carefully worked through the logic of quantum theory. He pointed out that, according to the equations, the collapse of the wave function, that moment when a fuzzy cloud of probabilities becomes a single concrete outcome, was not accounted for by the mathematics itself. Instead, it had to be assumed as a separate step. Von Neumann argued that any physical measuring device is itself made of atoms, and therefore also follows the laws of quantum mechanics. If you try to describe the act of measurement by including the measuring device in your equations, you end up pushing the problem one step further back. What then causes the collapse? His solution was bold. He suggested that the chain of measurement continues until it reaches something outside of physics, namely consciousness. In this view, the observer's mind plays a unique role in bringing about definite outcomes. Not long after, the physicist and mathematician Eugene Wigner carried this idea further. Wigner, who made key contributions to the understanding of symmetries in quantum physics, became a vocal proponent of the link between consciousness and wave function collapse. He proposed a thought experiment sometimes called Wigner's friend. In this scenario, Wigner imagines that his friend performs a quantum measurement inside a closed laboratory, while Wigner himself waits outside. From the friend's perspective, the measurement yields a definite result. But from Wigner's perspective, before he looks inside, the entire laboratory, including his friend, should be described as a superposition of possibilities. Only when Wigner opens the door and becomes aware of the outcome does the superposition collapse into a single reality. The implication was unsettling. If this reasoning were taken seriously, consciousness itself seemed to play a central role in determining reality. Until someone became aware of an outcome, the universe might remain suspended in a haze of possibilities. This was a dramatic departure from classical physics, where the world was assumed to exist in a definite state, whether or not anyone was looking. For many, this was less a scientific conclusion and more a philosophical temptation. It echoed ancient ideas about the mind-shaping reality, dressed in the new clothing of quantum mechanics. Wigner himself later stepped back from the stronger claims, admitting that his ideas about consciousness were speculative and perhaps more philosophy than physics. But by then the seed had been planted. The notion that the mind might be woven into the fabric of quantum reality captured imaginations far beyond the physics community. It is important to pause here and note that most working physicists did not embrace this interpretation. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, was far more modest. It treated the wave function as a tool for calculating probabilities rather than a literal description of reality. In this view, measurement causes collapse, but no special role for consciousness is required. The observer is simply part of the experimental setup, not a mystical participant in the creation of the universe. Nevertheless, the allure of von Neumann and Wigner's ideas lingered. They seemed to offer a scientific foothold for one of the deepest questions of existence: why there is a conscious mind at all. If physics required consciousness to make sense, then perhaps the two mysteries were intertwined. It was an idea that resonated not only with physicists but also with philosophers, mystics, and later popular writers who saw in it a bridge between science and spirituality. Yet blending physics and philosophy is a tricky business. Equations are precise while words can be slippery. When Wigner spoke of consciousness collapsing the wave function, was he making a testable claim, or was he using consciousness as a placeholder for something still poorly understood? Critics warned that treating the mind as a kind of magic wand that resolves quantum puzzles risked abandoning the rigor of science. If every unsolved question was answered with "consciousness did it," the field would quickly lose its explanatory power. Despite these criticisms, the speculation endured because it touched on something profound. Quantum mechanics had already dismantled our comfortable picture of a predictable, clockwork universe. If particles could exist in superpositions and influence each other across vast distances, then why not entertain the possibility that the mind, too, was part of this strange story? At the very least, the discussions of von Neumann and Wigner opened a philosophical door. Consciousness was no longer something easily dismissed as separate from physics. Even today, Wigner's friend remains a thought-provoking puzzle. Variations of the scenario continue to be debated in modern research, particularly in experiments that test the foundations of quantum mechanics. Although most physicists interpret the situation without invoking consciousness, the thought experiment underscores just how slippery the boundary between observer and system can be in the quantum world. Looking back, these early speculations remind us that the history of science is not always a straight march toward clarity. It is filled with detours, bold guesses, and ideas that hover between insight and imagination. Von Neumann and Wigner may not have solved the measurement problem, but they crystallized a question that still haunts physics. What does it really mean to observe the world? And perhaps just as important, who or what is the true observer? Whether one views their ideas as profound insights or philosophical overreach, they played a crucial role in shaping the conversation. They kept alive the possibility that consciousness might be more than a passive witness to the universe, that it could, in some mysterious way, be an active participant. And even if the physics community largely set aside these speculations, the cultural and intellectual fascination with them has never quite faded. In the late 20th century, the idea of linking consciousness to quantum mechanics found new champions in an unlikely pair: a world-renowned mathematical physicist and a practicing anesthesiologist. Roger Penrose and Stuart Hameroff came from very different backgrounds, yet together they developed one of the most elaborate and controversial theories of quantum consciousness: orchestrated objective reduction, often shortened to OR. Roger Penrose was already a legend in mathematical physics. He made groundbreaking contributions to general relativity, black holes, and the geometry of space and time. His work with Stephen Hawking helped show that singularities, points of infinite density, were not just mathematical curiosities but real features of the universe. Penrose was known for his fearless willingness to tackle deep, foundational questions. For him, consciousness was one of the greatest mysteries of all, and he doubted that conventional neuroscience could ever fully explain it. Stuart Hameroff, on the other hand, approached the problem from the world of medicine. As an anesthesiologist, he had spent his career studying how chemicals could turn consciousness off and on, sometimes in a matter of seconds. He became fascinated with the fine structures inside neurons called microtubules. These tiny cylindrical scaffolds help maintain the shape of cells and play important roles in cell division and transport. Hameroff wondered whether they might also be doing something far more exotic inside the neurons of the brain. When Penrose and Hameroff connected in the early 1990s, their ideas fused into the OR model. The basic claim of the theory is that microtubules inside brain cells are capable of supporting delicate quantum processes, and that these processes give rise to conscious experience. Penrose brought the physics, proposing a new kind of quantum collapse he called objective reduction. Hameroff brought the biology, suggesting microtubules as the structures that could orchestrate these collapses inside neurons. Objective reduction was Penrose's answer to the measurement problem. Instead of saying collapse happens when an observer looks, or that it never really happens at all, Penrose proposed that gravity itself sets a limit on superposition. When a quantum system involves significantly different distributions of matter and energy, the fabric of space-time becomes unstable, and the superposition resolves into one outcome. In other words, the universe chooses a reality based on a fundamental threshold, independent of any human observer. Hameroff suggested that microtubules in neurons were perfectly placed to take advantage of this process. He argued that their regular, lattice-like structures could protect quantum states from environmental noise long enough for OR events to occur. These orchestrated reductions, he claimed, would then provide the raw moments of awareness that combined to form the continuous stream of consciousness. The theory was bold, imaginative, and for many irresistible. It offered a way to connect the deepest mysteries of the mind with the strange rules of quantum physics. It also seemed to explain why anesthesia works. Perhaps it disrupts quantum processes in microtubules, shutting down consciousness directly at its source. To those intrigued by the possibility that consciousness might be something more than computation, OR was a tantalizing glimpse of a hidden layer of reality. But for all its appeal, OR has faced fierce skepticism. Most neuroscientists point out that the brain is a warm, wet, and noisy environment. Quantum states, especially delicate ones involving superposition, are notoriously fragile. In laboratories, quantum experiments usually require extreme isolation and temperatures close to absolute zero to protect them from decoherence, the rapid loss of quantum coherence when interacting with the environment. Expecting such fragile states to persist in the heat and bustle of a biological brain strikes many as unrealistic. Others note that microtubules, though fascinating structures, are primarily understood as components of the cytoskeleton, responsible for transport and support within cells. While they are complex and capable of dynamic behavior, there is little direct evidence that they play any role in processing information at the level needed for consciousness. The leap from cell biology to orchestrated quantum events is vast. Critics also point out that OR has not generated clear, testable predictions that would distinguish it from other theories of consciousness. Science thrives on falsifiability, the ability to design an experiment that could prove a theory wrong. Without specific testable claims, a theory risks drifting into the realm of speculation rather than science. For many in neuroscience, OR feels too vague, too ambitious, and too ungrounded in evidence to be convincing. Even so, Hameroff and Penrose have defended their theory with persistence. They argue that some evidence points toward the plausibility of quantum effects in biology. For instance, in photosynthesis, plants appear to use quantum coherence to transfer energy with remarkable efficiency. Birds may navigate using quantum entanglement in their retinas. If nature has found ways to use quantum mechanics in other biological systems, perhaps it could also do so in the brain. Supporters of OR also highlight intriguing findings in neuroscience. Some studies suggest that anesthetics do interact with microtubules, though interpretations remain debated. Penrose and Hameroff have also proposed ways that quantum vibrations in microtubules could be detected experimentally, although results so far remain inconclusive. What makes OR so captivating is not just the specifics of the model, but the way it bridges disciplines. It brings together physics, biology, philosophy, and even questions about the very nature of reality. It dares to suggest that consciousness is not just a byproduct of neural computation, but is tied to the fundamental structure of the universe. To those who find reductionist explanations of the brain unsatisfying, this theory provides a refreshing alternative, even if it may be more aspiration than demonstration. The skepticism, though, remains healthy. It is a reminder that while bold ideas can be inspiring, science requires more than inspiration. Theories must withstand scrutiny, produce evidence, and survive the harsh light of experimental testing. Many neuroscientists continue to believe that the brain's complexity, rather than exotic quantum effects, is enough to explain consciousness. In their view, OR is a captivating story but not yet a scientific breakthrough. Still, one cannot deny the imaginative power of the idea. The image of quantum processes flickering inside microscopic scaffolds in your brain has a certain beauty. Whether or not it turns out to be true, it speaks to a deep human desire, the wish for our minds to be connected to the deepest fabric of the cosmos. It reminds us that science is not only about answers, but also about the courage to ask questions that lie at the very edge of what we know, and in that spirit, OR continues to spark curiosity and debate. It may never be proven, or it may one day find surprising support. For now, it stands as one of the most daring attempts to weave the mysteries of the quantum world with the mystery of being conscious, a theory perched delicately between science and philosophy, just as fragile, perhaps, as the quantum states it imagines. There is a reason why the idea of a quantum brain refuses to fade away, despite skepticism. On the surface it may seem far-fetched, but when people look closely at how unusual the mind is compared to other natural phenomena, the possibility starts to feel less like fantasy and more like a door worth leaving ajar. To many, consciousness seems too rich, too unpredictable, and too creative to be the result of purely classical mechanics. Quantum mechanics, with its shimmering probabilities and leaps beyond determinism, has a kind of resonance with the way our inner lives actually feel. One of the main arguments in favour of a quantum brain is coherence. In quantum physics, coherence refers to the ability of a system to maintain a superposition of states without collapsing into one outcome. In most environments, coherence is fleeting. A particle exposed to heat, vibration, or random interactions with its surroundings loses its quantum character almost instantly. But nature has surprised us. In recent decades, researchers have discovered that certain biological systems can preserve coherence far longer than expected. Photosynthesis is a striking example. When light strikes the pigments inside plant cells, the energy must travel efficiently to reaction centers, where it can be converted into chemical fuel. Experiments suggest that this transfer does not occur in a simple step-by-step fashion. Instead, the energy appears to explore multiple paths simultaneously through quantum coherence, finding the most efficient route. The fact that plants, quietly performing their daily work under the sun, might be using quantum tricks has convinced some scientists to look more seriously at other parts of biology. If leaves can do it, why not neurons? Microtubules and other complex structures in the brain could, in theory, shelter quantum processes. While no one has shown definitively that this happens, the discovery of quantum effects in unexpected places has softened the old certainty that brains were too warm and noisy to allow such phenomena. The brain, after all, is an extraordinarily complex organ, consuming vast amounts of energy and coordinating trillions of connections. It is at least plausible that it has found ways to harness subtle effects we do not yet fully understand. Another reason quantum ideas appeal in the study of the brain is complexity itself. Classical physics is built on predictability. If you know the position and momentum of a ball, you can calculate where it will land. But minds do not behave like billiard balls. Human thought is messy, non-linear, and full of leaps that defy simple prediction. You may start thinking about dinner, get reminded of a childhood memory, and then suddenly find yourself wondering about the meaning of life, all in the space of a few seconds. The path is not linear, and the outcomes are difficult to anticipate. This unpredictability, some argue, feels more at home in a quantum framework than in a classical one. Quantum mechanics is built around probabilities, not certainties. A particle's path is not determined until it is measured, and even then outcomes are inherently uncertain. That same quality of indeterminacy resonates with the feeling of free will. If our brains were nothing but classical machines, chugging along according to predetermined laws, then perhaps every choice we make would already be set in stone by the initial conditions of the universe. But if quantum processes play a role, then there is room for genuine novelty, for decisions that are not strictly determined but influenced by probabilities. This connection to free will is deeply attractive. People often resist the idea that consciousness is just an elaborate illusion generated by deterministic neurons. To imagine that each thought, each act of creativity, or each spark of inspiration might involve a dance of quantum possibilities adds a layer of wonder. It makes creativity feel not just like clever computation, but like something rooted in the fundamental uncertainty of the universe itself. The idea that when you write a poem, paint a picture, or have a sudden insight, you are riding the probabilities of quantum states. Well, that has a poetic ring to it, and it is easy to see why it captures imaginations. Supporters of the quantum brain hypothesis also point to the sheer scale of information processing in the human mind. A typical brain contains around 86 billion neurons, each connecting to thousands of others. The number of possible connections is staggeringly large, rivaling the number of stars in the galaxy. With so much complexity, it is tempting to think that ordinary physics might not be enough to capture the full picture. Quantum mechanics, with its ability to handle superpositions of possibilities, might be the only framework capable of explaining the richness of thought. There is also the matter of creativity and insight, which often arrive in ways that feel less than mechanical. Many people describe moments of inspiration as sudden, almost magical, as though ideas leap from nowhere. Quantum processes, with their ability to sample multiple possibilities simultaneously, seem like an appealing metaphor for this. Instead of plodding through ideas one at a time, perhaps the brain, at some hidden level, explores many possibilities at once, collapsing into a fresh insight when conditions are right. Of course, none of these arguments amount to proof. They are suggestive parallels, more philosophical than empirical. But they highlight why the idea continues to surface in serious discussions, despite the lack of direct evidence. Quantum mechanics provides a language that matches the strangeness of consciousness, a language where unpredictability and possibility are not flaws but fundamental features. And perhaps there is a deeper reason why people are drawn to the thought of a quantum brain. It makes our inner lives feel directly connected to the fabric of reality. If consciousness was simply a matter of classical computation, it might seem like a machine's output, impressive but ultimately mundane. If instead it arises from the same principles that govern the birth of stars and the behavior of particles, then it feels elevated, almost cosmically significant. The brain becomes not just a lump of biological tissue, but a stage where the deepest rules of the universe play out in the form of awareness. Even if the idea turns out not to be true, it has value as a way of expanding imagination. Science progresses not only through strict data, but also through bold hypotheses that inspire investigation. The belief that the brain might use quantum tricks encourages researchers to look more closely at biology, to search for hidden processes, and to test the boundaries of what we think is possible. And even if the experiments never confirm it, the act of asking the question enriches our understanding of both physics and the mind. In the end, the arguments for a quantum brain rest on coherence, complexity, unpredictability, and the irresistible pull of free will and creativity. They may not prove the case, but they make it clear why the idea has such enduring charm. It suggests that within the quiet folds of the brain, the same strangeness that governs the cosmos might also flicker, that each thought is not only a product of biology, but perhaps a whisper of quantum possibility. For all the intrigue that comes with linking consciousness to quantum mechanics, there is an equally strong case against it. Many neuroscientists and physicists argue that the brain, remarkable as it is, does not need any quantum trickery to explain its workings. They suggest that the mystery of consciousness, while deep, can eventually be solved within the framework of classical biology and physics. And when one looks closely at the conditions required for quantum phenomena to thrive, the brain seems like one of the least likely places for them to occur. The first obstacle is decoherence. In physics, decoherence describes the process by which quantum states lose their fragile superpositions when they interact with the environment. To maintain quantum coherence, particles usually need to be isolated from outside disturbances, kept shielded from vibrations, noise, and especially heat. In laboratories, researchers often cool quantum systems down to near absolute zero in order to study them. Even then, coherence is difficult to preserve for more than a fraction of a second. Brains, by contrast, are anything but isolated. They are warm, wet, and noisy. Neurons fire continuously, ions flow across membranes, and chemical messengers drift through a soup of activity. Temperatures hover around body heat, fluids circulate, and the entire system pulses with energy and motion. To put it bluntly, the brain is the opposite of the quiet, controlled laboratory conditions needed for delicate quantum states. Expecting coherence to survive in this environment, some argue, is like expecting a soap bubble to remain intact in a thunderstorm. Another important point is scale. Quantum effects are easiest to observe in very small systems, like single particles or a handful of atoms. Brains, however, are macroscopic organs, made up of billions of neurons and trillions of synapses. While individual molecules inside neurons might display quantum behavior, scaling that up to account for the full richness of consciousness is a leap of many orders of magnitude. Critics argue that whatever quantum effects occur at the microscopic level are likely drowned out by the overwhelming complexity and noise of the system as a whole. Neuroscience also provides strong reasons to think that the brain functions perfectly well without any need for quantum mechanics. Decades of research have shown clear links between patterns of neural activity and mental states. For example, specific brain regions are associated with vision, language, memory, and emotion. Injuries or strokes in those regions reliably disrupt those abilities. Drugs and chemicals alter mood and perception in predictable ways by changing neurotransmitter activity. Electroencephalograms can record brainwaves that correlate with sleep, wakefulness, and attention. In all these cases, the brain's functions are explained by networks of neurons and the exchange of electrical and chemical signals. None of this requires invoking quantum processes. From this perspective, consciousness may be emergent rather than exotic. Emergence refers to the way complex systems can produce new properties that are not obvious from the individual parts. For example, a single water molecule is not wet, but a large collection of them produces the property of wetness. Similarly, individual neurons are not conscious, but their collective interactions give rise to awareness. In this view, the mystery of consciousness lies not in hidden quantum physics, but in the staggering complexity of neural networks. The challenge is to understand how the firing patterns of billions of neurons together create the unified experience of a mind. Critics of the quantum brain hypothesis also note that it risks being unfalsifiable. A good scientific theory should make predictions that can be tested. If the predictions fail, the theory should be abandoned or revised. With the quantum brain idea, however, predictions are often vague or difficult to test experimentally. Without clear evidence, the theory risks drifting into speculation. Neuroscientists emphasize that, while it's important to remain open to new ideas, one must also demand rigorous evidence before rewriting the foundations of biology. Another concern is that quantum explanations sometimes serve as placeholders for ignorance. The mind is undeniably mysterious, and it is tempting to reach for exotic physics to fill the gap. But history shows that mysteries often yield to more ordinary explanations as knowledge advances. Lightning was once thought to be divine anger, but it turned out to be electricity. Disease was attributed to curses until germs were discovered. The risk with quantum consciousness is that it becomes a kind of scientific mirage, impressive from a distance, but evaporating under closer inspection. Some neuroscientists also worry that the allure of quantum consciousness can distract from more promising avenues of research. Brain imaging technologies, computational models, and advances in neurobiology are steadily revealing how cognition and awareness arise from physical processes. These fields offer concrete progress, grounded in observable evidence. Diverting too much attention towards speculative quantum models, they argue, could slow down the practical work of understanding and treating the brain. There is also a philosophical caution here. Linking consciousness to quantum mechanics might be seen as shifting the mystery from one domain to another without really solving it. Quantum physics itself is puzzling and incomplete, so saying that consciousness comes from quantum effects may simply be exchanging one enigma for another. Instead of explaining why subjective experience exists, the claim risks restating the question in more exotic terms. Still, it is important to note that skeptics are not dismissing the wonder of consciousness. They simply believe that the existing tools of neuroscience, combined with classical physics, will eventually be enough. The fact that brain states correlate so tightly with mental states, that brain injuries so clearly affect consciousness, and that brain stimulation can reliably alter perception, suggests that the key lies in the physical structure and activity of the brain itself. And there is something elegant about this view. It suggests that consciousness is not a magical anomaly requiring new physics, but a natural product of evolution and biology. Just as the heart pumps blood and the lungs exchange oxygen, the brain generates awareness. The mystery lies in the details of how it does so, not in whether it needs special rules of reality to make it happen. The argument, then, is not that the brain is boringly classical, but that its complexity is enough to account for the richness of the mind. brains are among the most intricate systems in the known universe. They may not need quantum mechanics to explain their workings any more than thunderstorms need new laws of physics to explain lightning. Sometimes, the ordinary rules, when applied at immense levels of complexity, are extraordinary enough. In this light, the skeptical case is clear. Consciousness, they argue, is indeed mysterious, but it is not miraculous. It emerges from the vast, intricate dance of neurons, glia, and chemistry. It does not require superpositions inside microtubules or entanglement across synapses. It requires only that we keep studying the brain in ever greater detail, peeling back the layers until the mystery yields to understanding. Whether or not that final explanation will ever capture the essence of what it feels like to be conscious remains uncertain. But for many neuroscientists, the answer lies not in quantum physics, but in the extraordinary possibilities of biology itself. Quantum physics might sound like something reserved for physicists hunched over chalkboards or engineers tinkering with lasers, but in recent years scientists have uncovered evidence that nature itself may have been using quantum tricks long before humans ever discovered them. This surprising field, known as quantum biology, explores how living systems may take advantage of the weird rules of quantum mechanics. While the subject is still developing, a few striking examples have already emerged, showing that the strange can sometimes be found in the everyday. Perhaps the best-known case is photosynthesis, the process by which plants, algae, and some bacteria convert sunlight into chemical energy. On the surface, it seems straightforward. Light is absorbed by pigments, and the energy is passed along to reaction centers where it drives the production of sugars. But experiments probing the details of this process have revealed something unexpected. The energy transfer is astonishingly efficient, much more so than one might expect if it simply hopped from molecule to molecule in a random, stepwise fashion. Instead, evidence suggests that the energy exists in a quantum superposition as it moves, simultaneously sampling multiple pathways and settling on the most efficient route. In laboratory experiments with ultra-fast lasers, researchers have observed patterns of quantum coherence in light-harvesting complexes, hinting that these biological systems maintain delicate quantum states at warm temperatures. In other words, when you look at a leaf catching sunlight, you might be witnessing quantum mechanics at work in a garden. The idea that nature discovered a way to exploit coherence billions of years before human physicists struggled to preserve it in their labs is both humbling and inspiring. Another intriguing example comes from the animal kingdom, specifically in the navigation of birds. Many species migrate across vast distances with uncanny precision, often travelling thousands of kilometres without getting lost. One theory proposes that some birds use the Earth's magnetic field as a kind of invisible map. But how do they sense something so subtle? A leading hypothesis is that they rely on quantum entanglement inside proteins called cryptochromes, located in their eyes. According to this idea, when light hits the cryptochrome molecules, it excites pairs of electrons into entangled states. The orientation of these states is influenced by Earth's magnetic field, altering chemical reactions in a way the bird can detect. This effectively allows the bird to see magnetic fields superimposed over its vision, like a hidden compass. While research is ongoing, behavioral experiments support the idea that disrupting entanglement could interfere with a bird's ability to navigate. If true, it would mean that tiny quantum effects help guide creatures across continents. The sense of smell provides yet another possible example of quantum biology. The traditional explanation for olfaction is that odorant molecules fit into receptors in the nose like keys in locks, triggering signals to the brain. While this explains much, it leaves certain puzzles unsolved. For instance, some molecules with nearly identical shapes smell very different, while others with different shapes smell strikingly similar. An alternative theory suggests that smell may involve not just shape, but also quantum vibrations. In this model, odorant molecules vibrate at specific frequencies. When bound to receptors, these vibrations may allow electrons to tunnel across a gap, a distinctly quantum process. This tunneling could be what triggers the neural signal, providing a mechanism that explains the quirks of smell more neatly than the shape-only model. While this theory is debated, it highlights how even the act of sniffing a flower might involve phenomena that reach into the quantum world. These examples do not mean that biology is generally quantum in the way some enthusiasts imagine. The conditions that allow coherence or entanglement to persist in living systems are rare and specialized. Photosynthesis, for instance, may use specific molecular structures designed by evolution to shield quantum states just long enough to be useful. Birds may rely on highly specialized proteins fine-tuned for navigation. Smell, if the quantum theory holds true, would be another case of evolution seizing upon subtle physics for a practical purpose. What these cases do show is that quantum mechanics is not confined to laboratories and particle accelerators. Life has always been an opportunistic experimenter, taking advantage of whatever laws the universe provides. If quantum rules can improve efficiency or provide a new sense, evolution may find a way to exploit them. This realization has softened some of the earlier skepticism about the role of quantum physics in living systems. The discovery of coherence in photosynthesis, for instance, once seemed impossible in warm, wet environments, and yet plants appear to manage it daily. It is not hard to see why these findings encourage speculation about the brain. If quantum mechanics can play a role in processes as varied as harvesting light, sensing magnetism, and distinguishing smells, then perhaps it could also play a role in the rich and mysterious phenomenon of consciousness. The brain is, after all, an organ of staggering complexity, consuming large amounts of energy and coordinating signals with exquisite precision. If any biological system were to shelter quantum effects in a useful way, the brain seems like a natural candidate. Still, it is important to remain cautious. The confirmed cases of quantum biology involve processes on the level of molecules and proteins, where the timescales and conditions are carefully balanced. Extending this to something as large and noisy as the brain is a leap that requires evidence we do not yet have. Consciousness is not just a chemical reaction or a transfer of energy, but a whole orchestra of processes unfolding across billions of neurons. Whether quantum mechanics is playing a hidden instrument in the orchestra remains an open question. And yet, the discoveries in quantum biology invite us to keep the door open. They remind us that nature is cleverer than our assumptions, that the universe sometimes hides its most delicate rules inside the ordinary. A leaf in the sun, a bird on the wing, a fragrance drifting through the air. Each of these might be a quiet stage where quantum mechanics performs, unseen but essential. If such strangeness can appear in these places, then perhaps it's not so far-fetched to wonder if it also plays some part in the grander mystery of the mind. Whether or not consciousness turns out to be quantum, the exploration itself enriches our understanding of life. It shows that biology is not just chemistry scaled up, but a tapestry woven from the deepest threads of physics. And in that tapestry, there may still be patterns we have yet to see, waiting patiently in the quiet interplay between the living and the quantum world. At the very heart of quantum mechanics lies a question that has fascinated, baffled, and occasionally frustrated generations of scientists. What exactly causes a quantum system to collapse into a definite outcome? In the quantum world, particles exist as wave functions, mathematical descriptions of probabilities. An electron is not in one exact place, but spread out in a haze of possibilities. A photon is not in one path, but in a superposition of many. Yet whenever we measure these particles, the possibilities vanish and we see one outcome. This sudden shift is called wave function collapse, and it raises an unsettling puzzle. Why does measurement make the universe decide? One answer, proposed in the early days of quantum theory, was that consciousness itself might be the trigger. If the act of observing a system forces it into a definite state, then perhaps the conscious observer plays a direct role in shaping reality. This idea became known as the observer problem, and it remains one of the most tantalizing intersections of physics and philosophy. It is easy to see why the notion has such appeal. Imagine a particle existing in two possible places at once. If the universe must choose only when you look at it, then your awareness seems to have cosmic influence. It suggests that consciousness is not just a passive spectator, but an active participant in the unfolding of reality. In this picture, every act of perception is also an act of creation. That is a profoundly empowering thought, and it resonates strongly with mystical traditions that have long claimed the mind shapes the world. This interpretation has been a favourite among poets, spiritual thinkers, and even some physicists who are willing to speculate beyond strict evidence. It carries a certain poetry. Reality remains unformed until illuminated by awareness, like a stage waiting for the spotlight of consciousness. Some have taken it further, suggesting that the collective minds of all observers might weave together the fabric of the cosmos, collapsing wave functions into the shared world we inhabit. But as evocative as this sounds, most physicists are cautious, if not outright dismissive of this view. The problem is that the equations of quantum mechanics make no special mention of consciousness. They describe particles, probabilities, and interactions. The word observer in the original formulations was never meant to imply a human mind. In fact, almost anything that interacts with a quantum system can count as an observation. A photon hitting a detector, an atom bumping into another atom, even the surrounding environment, all of these interactions can force a system to lose its superposition and behave classically. This process is better understood today through the theory of decoherence. When a quantum system interacts with its environment, information about its state leaks out, effectively destroying the delicate superposition. What looks like collapse may simply be the unavoidable result of entanglement with the surroundings. In this view, wave functions don't need a conscious observer to collapse. They collapse whenever they interact with anything else. Your awareness, while important to you, is not required by the physics. Still, the role of the observer continues to haunt discussions of quantum theory. Part of the difficulty is that quantum mechanics does not fully explain why one outcome occurs rather than another. It gives probabilities, not certainties. The mathematics tells us that a particle has, for example, a 50% chance of being here and a 50% chance of being there, but it does not tell us why. In this specific instance, it appeared here. Some interpretations dodge the question entirely, treating the wave function as just a tool for prediction, not a literal object that needs to collapse. Others invent new layers of reality, like the many worlds interpretation, which suggests that all outcomes happen, each in its own branching universe. Because the physics leaves room for interpretation, consciousness has repeatedly been smuggled back into the story. After all, humans are the ones asking the questions, writing down the equations and interpreting the results. It is tempting to think our minds must be part of the machinery. When we stare into the quantum haze, perhaps it is our awareness that pulls the probabilities into a single reality. Mystical traditions love this line of thought, because it blurs the boundary between self and cosmos. If observing the world shapes it, then perhaps meditation, intention, or collective consciousness could influence reality at the deepest level. Books and popular science programs often run with this idea, sometimes far beyond what the actual physics supports. It makes for a compelling story. The universe is participatory, and you are one of its creators. The scientific community, however, is largely unconvinced. Physicists tend to prefer explanations that do not require special roles for human minds. After all, the universe got along just fine before humans arrived. Stars formed, planets spun, and atoms collided long before there was anyone to look at them. Suggesting that consciousness is required for reality risks sliding into solipsism, the view that the world only exists when observed, which does not sit well with the mountains of evidence for a universe that evolved independently of us. This does not mean that the observer problem has been fully solved. The measurement problem remains one of the great unsolved puzzles of quantum theory. Even with decoherence, questions linger about why we experience definite outcomes instead of a blurred mix of possibilities. Consciousness may not be the answer, but the mystery is real. The debate highlights a broader truth about science. Sometimes our theories work perfectly in practice, while leaving us philosophically unsatisfied. Quantum mechanics predicts experimental outcomes with breathtaking accuracy. Yet when we ask what the mathematics means, we find ourselves in a maze of interpretations. Into that maze, consciousness often wanders, bringing with it both inspiration and confusion. For now, the safest statement is that there is no evidence that human awareness collapses wave functions. Quantum systems behave as they do because of the mathematics and interactions with their environments, not because someone happens to be watching. But the persistence of the observer problem shows that people hunger for a deeper connection between mind and world, and quantum mechanics provides fertile ground for such imaginings. Whether or not consciousness has any role in collapse, the idea itself continues to inspire. It reminds us that science and philosophy often travel together, that equations can stir the same sense of wonder as poetry, and that mysteries at the edge of knowledge are places where curiosity thrives. Even if the observer is not the creator of reality, the act of observing, of asking questions, of seeking to understand, is one of the most profoundly human things we can do. The measurement problem is one of those puzzles that makes quantum mechanics feel less like a neat set of equations and more like an unfinished riddle. The mathematics says that a particle can exist in a superposition of states, with its position, momentum, or spin described as a cloud of probabilities. Yet the moment we measure it, the haze vanishes and a single outcome appears. Why should measurement hold such power? Why does the world of possibilities narrow to one definite reality when an observation is made? And what exactly counts as a measurement? These questions are at the heart of the measurement problem, and they have inspired a host of interpretations, each trying to make sense of how the quantum world becomes the everyday one we experience. The most famous and historically influential response is the Copenhagen interpretation, named after the city where Niels Bohr and Werner Heisenberg worked in the 1920s. According to this view, the wave function is not a literal picture of reality, but a mathematical tool for predicting outcomes. The particle is not really in two places at once. Rather, the wave function encodes the probabilities of finding it here or there. Collapse occurs not because of some mystical process, but because measurement is the point where quantum possibilities give way to classical facts. In this interpretation, the observer plays a role, but not necessarily a conscious one. Any measuring device that interacts with the system counts as an observer. The Copenhagen view is pragmatic. It tells physicists how to calculate results, and reminds them not to worry too much about what is really happening. Pragmatic, however, does not mean philosophically satisfying. Critics of Copenhagen point out that it leaves a gap between the quantum description and the classical world we see. Where exactly is the dividing line? Does collapse happen when an electron hits a detector, when the detector registers a signal, when a human looks at the display? The Copenhagen view never fully clarifies this, leading some to accuse it of sweeping the mystery under the rug. In contrast, the many worlds interpretation, proposed by Hugh Everett in the 1950s, takes a radically different approach. According to this view, the wave function never collapses at all. Instead, all possible outcomes happen, each in its own branch of the universe. When you measure a particle that could be in two states, reality splits, and there are now two versions of you, each seeing a different result. These branches do not interact, so from your perspective it looks as though collapse occurred, but in truth the universe simply grew larger, accommodating every possibility. The appeal of many worlds is that it removes the special role of measurement. The wave function evolves smoothly, according to the equations of quantum mechanics, with no abrupt collapse. The downside is that it multiplies reality into an almost unimaginable number of universes, with new branches constantly being created. Some find this extravagant, while others argue it is simply the price of consistency. To its supporters, many worlds is elegant because it does not require any ad hoc rules. To its detractors, it feels like trading one mystery for another, expanding the cosmos into a sprawling multiverse to avoid a collapse no one fully understands. Another alternative is the pilot wave theory, also known as de Broglie-Bohm mechanics. In this interpretation, particles always have definite positions, guided by an invisible wave. The wave evolves according to the Schrödinger equation, while the particle rides along like a surfer on the sea. Measurement does not cause collapse because the particle was always in a specific place. The wave simply steered it there. This view restores determinism to quantum mechanics, giving particles definite properties at all times. Pilot wave theory has its own challenges. It requires a hidden layer of reality not directly observable, and it introduces non-local effects, meaning that changes in one place can instantly influence another. While the mathematics works, the theory has not gained as much acceptance as Copenhagen or many worlds, partly because it feels like adding extra machinery to a system that already functions. Across all these interpretations, one theme is clear: consciousness is not required. The measurement problem arises not because human minds are special, but because quantum theory itself is incomplete in how it describes the transition from probabilities to actual events. Modern physics explains collapse in terms of decoherence, the interaction of quantum systems with their environments. When a particle interacts with countless atoms, its delicate superposition rapidly unravels, leaving only the classical outcome we observe. Consciousness plays no role in this process. Yet despite this, the language of observers has always made it tempting to imagine that the mind matters. The very word measurement implies someone doing the measuring, which opens the door to interpretations where awareness becomes fundamental. For those drawn to mysticism or philosophy, this is irresistible. Perhaps the act of observation by a conscious mind does collapse wave functions, weaving reality from possibility. Physicists, however, remain cautious. The history of science is filled with examples of human-centered explanations that later proved unnecessary. The Earth once seemed like the center of the cosmos, until astronomy showed otherwise. Life once seemed to require a mysterious vital force, until biology revealed chemistry at its core. Consciousness may be the next frontier, where a human-centered view gives way to a more universal explanation. In the end, the measurement problem remains unsolved, but not for lack of trying. Copenhagen offers a pragmatic way forward. Many worlds removes collapse entirely, and pilot wave introduces hidden guidance. None has been universally accepted, which means the question of how the quantum world becomes the classical one is still open. What these interpretations do share is a refusal to grant consciousness a privileged role. The brain may be mysterious, but in physics, measurement is something any physical interaction can accomplish. This does not make the observer problem less fascinating. It continues to remind us that even our most successful theories leave room for wonder, ambiguity, and imagination. Whether the universe collapses, branches, or guides particles along hidden waves, it is still a reality stranger than common sense suggests. Consciousness may not decide outcomes, but it does decide to ask questions, and perhaps that, in itself, is its greatest role in the quantum story. When people first hear about the possibility that consciousness might be linked to quantum mechanics, it sounds like a natural match. Both are mysterious, both are strange, and both resist simple explanations. But many neuroscientists argue that this is a case of two enigmas being forced together without necessity. To them, the brain already contains everything needed to generate awareness, without borrowing exotic tricks from subatomic physics. Consciousness, they suggest, may be extraordinary, but it is not supernatural, and it certainly does not require rewriting the laws of biology. One of the strongest points in favour of a classical explanation for consciousness is the enormous progress neuroscience has already made. Over the past century, researchers have traced thought, emotion, and memory to specific regions and circuits in the brain. The visual cortex processes what you see, the hippocampus consolidates memories, the amygdala shapes fear and emotion, and the prefrontal cortex guides planning and decision-making. Electrical activity in these regions correlates tightly with mental states. When neurons in certain areas are stimulated, they can induce sensations or movements. When regions are damaged, the abilities they support are impaired or lost. These are not vague associations. They are robust, repeatable findings that show the mind depends directly on brain structure and activity. The brain's behavior also follows clear principles of computation and communication. Neurons exchange signals using electrical impulses called action potentials. These spikes travel down axons, jump across synapses, and trigger chemical messengers that activate other neurons. Networks of these connections form circuits that integrate information. At any given moment, billions of neurons are firing in intricate patterns, producing waves of activity that can be measured with electrodes or brain imaging techniques. Electroencephalograms, for example, reveal brain waves that change with sleep, wakefulness, and attention. Functional MRI scans show how regions light up during tasks like reading, remembering, or imagining. None of this requires invoking quantum physics. Another powerful concept is emergence. Emergent behavior occurs when complex systems display properties not obvious from their individual parts. Water molecules are not wet, but a collection of them creates the sensation of wetness. Ants are simple creatures, but their colonies display complex social organization. In the same way, consciousness may be an emergent property of networks of neurons. Individual neurons are not conscious, but their coordinated activity gives rise to awareness. This view does not diminish the mystery of consciousness. Instead, it places it within the framework of complexity science. The brain, with its 86 billion neurons and trillions of connections, is one of the most complex systems known to exist. If anything is capable of producing new properties through emergence, it is the brain. Skeptics of quantum consciousness also point out that determinism does not rob us of richness. The unpredictability and creativity of human thought can arise from classical systems without needing quantum uncertainty. Chaotic dynamics in classical physics can create behavior that is effectively unpredictable, even if it follows strict rules. The weather, for example, is governed by classical equations, yet its complexity makes it notoriously difficult to forecast beyond a few days. Similarly, the brain may follow deterministic processes at the level of neurons, while still producing thought patterns that feel free, creative, and novel. Complexity itself is enough to generate surprise. Another reason neuroscientists remain confident in classical explanations is the ability to manipulate consciousness directly. Anesthetics can reliably switch awareness off and on, acting on neurotransmitter systems in the brain. Psychedelic drugs alter perception by binding to serotonin receptors. Electrical stimulation can evoke sensations or trigger memories. Sleep cycles can be tracked through predictable shifts in brain activity. These findings strongly suggest that consciousness arises from biological chemistry and circuitry. If fragile quantum states were required, it would be difficult to explain why such crude tools work so consistently. Furthermore, the brain's design seems optimized for redundancy and reliability rather than delicate quantum processes. Neurons often fire in patterns of large groups, ensuring that signals are transmitted robustly even if individual neurons fail. Synaptic transmission, though probabilistic, is reliable enough to support learning and memory. If consciousness depended on fragile quantum coherence, it would be puzzling how awareness could survive the noise, heat, and constant molecular jostling of the brain. From a biological standpoint, evolution tends to favor sturdy mechanisms, not delicate ones. This line of reasoning offers comfort to those wary of stretching physics too far. It reassures us that no exotic new forces or hidden dimensions are required to explain the mind. The challenge is enormous, but it is a challenge within the reach of biology, psychology, and neuroscience. The tools we already have, from brain imaging to computational models, are steadily revealing more of the picture. As knowledge deepens, the gap between brain activity and subjective experience may narrow without invoking quantum mysteries. Of course, this does not mean that consciousness is simple. It is still one of the hardest problems in science, and skeptics acknowledge that we are far from a full explanation. But pointing to quantum mechanics as the missing piece can feel like giving up on the complexity of biology too soon. Consciousness may not be weird because it requires strange new physics. It may be weird because the brain is astonishingly intricate, and we are only beginning to map its patterns. There is also a philosophical elegance in the classical view. It suggests that consciousness, as extraordinary as it feels, is a natural product of evolution. Just as wings evolved to harness air, and eyes evolved to capture light, brains evolved to process information, and, in doing so, generated awareness. It is not a miracle, but a feature of matter arranged in a particular way. To understand it fully may take decades or even centuries, but it does not demand rewriting the basic laws of the universe. In short, the skeptic's reassurance is this: consciousness is real, mysterious, and beautiful, but it does not need quantum weirdness to exist. The strangeness of quantum mechanics belongs to the world of particles and probabilities. The strangeness of consciousness belongs to the complexity of biology. Both are marvels in their own right, and both deserve study. But they do not have to be fused together to remain wondrous. And perhaps there is something calming in that thought. It means that consciousness does not dangle precariously on the edge of exotic physics, but rests firmly in the same world that gives rise to every other natural phenomenon. It is part of the grand continuum of life and matter, complex enough to dazzle us without needing to be magical. That may not sound as flashy as a quantum brain, but it is no less extraordinary that out of atoms, molecules, and neurons emerges the astonishing fact of awareness. The mystery of consciousness has never belonged solely to science. Long before brain scans and quantum equations, philosophers were puzzling over what it means to be aware and whether the mind is something separate from the body or simply another aspect of the physical world. In some ways, the debates we have today about quantum consciousness are simply new versions of very old questions, dressed up in modern scientific language. The players have changed, but the themes remain familiar. Is consciousness fundamental, or is it emergent? Is it separate from matter, or identical to it? One of the oldest and most enduring positions is dualism, the idea that mind and body are two distinct substances. The most famous champion of this view was René Descartes in the 17th century. For Descartes, the body was a machine, operating by mechanical laws, while the mind was immaterial, capable of thought and self-awareness. I think therefore I am was his way of grounding existence in the undeniable reality of conscious thought. Dualism offered a neat way to preserve the uniqueness of human awareness, while still allowing science to explain the physical world. But it came with a problem. How does something immaterial interact with something material? If the mind is not made of atoms, how does it move the body, influence speech, or cause a hand to reach for a cup of tea? Materialism, sometimes called physicalism, emerged as the counterpoint. According to this view, everything that exists is physical. Consciousness, no matter how mysterious it feels from the inside, arises from material processes in the brain. In this framework, neurons and chemistry are enough. No extra ingredients are required. Materialism gained strength as science advanced, showing again and again that phenomena once attributed to spirits or souls could be explained by physical causes. The heart pumps blood, digestion is chemistry, lightning is electricity, and so on. For materialists, consciousness is the last great mystery to yield to this approach, not an exception to it. Between these poles lies panpsychism, a view that has enjoyed a revival in recent years. Panpsychism suggests that consciousness is not something that suddenly emerges when matter becomes complex enough, but something intrinsic to matter itself. According to this perspective, everything has some degree of inner experience, from atoms to humans. A rock may not be conscious in any meaningful way, but the particles that compose it might have the tiniest glimmer of awareness. Panpsychism sidesteps the leap from non-conscious matter to conscious beings by making consciousness fundamental, woven into the very fabric of the universe. Each of these positions comes with its strengths and weaknesses. Dualism preserves the mystery of consciousness, but struggles with the problem of interaction. Materialism provides a clean, scientific framework, but often leaves people unsatisfied, since it reduces the vividness of subjective experience to mere mechanics. Panpsychism offers an elegant middle ground, yet critics accuse it of being too generous with consciousness, handing it out to electrons and quarks without explaining how simple proto-experiences combine into the rich awareness humans enjoy. Where then does quantum physics fit in? In many ways, it provides a new stage for these old debates. For dualists, quantum mechanics offers a realm where classical determinism breaks down, leaving space for mind to influence matter. The collapse of the wave function, mysterious as it is, seems like a potential opening for consciousness to exert control. For materialists, quantum mechanics is still physics, and even if it is probabilistic rather than deterministic, it remains a natural process that does not require extra substances. And for panpsychists, the strangeness of the quantum world, particles existing in superpositions connected across distances, provides a natural metaphor for the idea that consciousness is fundamental and ubiquitous. Quantum mechanics also complicates the conversation by introducing new philosophical puzzles of its own. If the universe is fundamentally probabilistic, what does that mean for free will? If particles exist in superpositions, does consciousness do the same? If entanglement connects particles across space, could minds also be entangled in ways we do not yet understand? These questions do not prove anything, but they fuel a lively dialogue between science and philosophy. Some thinkers have even suggested that panpsychism and quantum physics might be two sides of the same coin. If consciousness is a fundamental property of reality, then perhaps it shows up in the peculiar behaviours of the quantum world. The interconnectedness of entanglement, the fuzziness of superposition, the limits of certainty, all of these could be hints that awareness is not an afterthought of evolution, but part of the bedrock of existence. Whether or not this is true, it highlights how quantum theory has given ancient philosophical ideas new life. Skeptics caution that it's easy to get carried away with these parallels. Quantum mechanics is a precise mathematical framework, while philosophical concepts like mind and awareness are slippery and ill-defined. To equate the two too quickly risks confusion. Yet even skeptics admit that philosophy has a role to play, because science alone cannot always capture the lived reality of consciousness. Equations may describe particles, but they do not tell us what it feels like to taste sweetness or to hear music. Philosophy gives us the language to wrestle with those subjective aspects, even if it does not provide final answers. It is also worth noting that these debates are not just academic exercises. They influence how people think about themselves and the world. Dualism, for example, has historically supported religious ideas about souls and the afterlife. Materialism often aligns with scientific naturalism, emphasizing that humans are part of the same physical continuum as everything else. Panpsychism, with its insistence that awareness pervades reality, can inspire a sense of connection to the natural world, encouraging people to see consciousness not as rare and privileged, but as widespread and fundamental. Quantum physics, by shaking up our intuitions about reality, has only deepened these conversations. It reminds us that the universe does not always obey common sense, that particles can behave like waves, that outcomes can be probabilistic, and that connections can defy distance. In such a universe, perhaps consciousness is stranger than we imagine too. Whether one leans toward dualism, materialism, or panpsychism, the quantum stage invites us to reconsider old arguments with fresh eyes. In the end, the philosophy of possibility is about more than proving one position right. It's about keeping the mystery of consciousness alive in our thinking, allowing space for wonder while striving for clarity. Consciousness could turn out to be an emergent property of neurons, an irreducible feature of matter, or something entirely different? What is certain is that the debate has been with us for centuries and will likely continue as long as humans are asking questions, and perhaps that is fitting. For just as the quantum world resists being pinned down to one interpretation, so too does the inner world of consciousness resist being reduced to a single philosophy. Both remain open fields of possibility, inviting exploration and imagination alike. For all the fascination surrounding quantum consciousness, science lives and dies by evidence. Theories may be bold, ideas may be dazzling, but in the end they must meet the test of experiments. If quantum mechanics really plays a role in the brain, then it should leave traces we can detect. Researchers have been probing for these signs for decades, with some tantalizing hints but no conclusive proof. The story of these efforts is as much about the difficulty of testing as it is about the results themselves. One of the central lines of investigation comes from the OR theory of Penrose and Hameroff, which places microtubules at the heart of the matter. Microtubules are cylindrical protein structures that act as scaffolding within cells and help transport materials. In neurons, they play a role in shaping the cell and guiding the movement of molecules. According to OR, however, they may also serve as sites for quantum coherence, orchestrating the collapse of wave functions in a way that generates conscious experience. To test this, researchers have looked for evidence of quantum states within microtubules. Some laboratory experiments have suggested that microtubules can exhibit unusual patterns of vibration, potentially consistent with quantum behavior. For example, certain studies using spectroscopy have reported resonances that might indicate coherent oscillations within microtubule proteins. Other work has explored whether anesthetics, known to switch off consciousness, interact with microtubules in ways that could disrupt such processes. These findings are intriguing, but they remain controversial. Measuring delicate quantum states in complex biological molecules is extremely challenging, and results are often difficult to reproduce consistently across different labs. Another challenge is that even if microtubules display coherence under certain conditions, that does not prove the coherence is robust enough to survive in the warm, noisy environment of the brain, or that it plays any meaningful role in awareness. Quantum coherence in biology has been confirmed in systems like photosynthesis, but those involve short-lived effects optimized by evolution for very specific purposes. Whether microtubules can achieve something similar inside neurons is still an open question. Beyond microtubules, brain imaging techniques have also been used to search for hints of quantum behavior. Technologies like electroencephalography and functional MRI allow scientists to measure patterns of neural activity across the brain. While these methods provide remarkable insights into how regions coordinate during thought, memory, and emotion, they have not revealed anything that requires quantum mechanics for explanation. The patterns of activation can generally be described in terms of classical networks of neurons communicating through well-understood electrochemical processes. Some researchers have proposed more exotic tests. For instance, if quantum entanglement were occurring in the brain, it might produce correlations in neural signals that could not be explained classically. Efforts have been made to analyze brainwaves for signs of such correlations, but so far the results have been inconclusive. The problem is partly technical. The brain is such a complex system, with so much noise and variability, that teasing out subtle quantum signatures is like trying to hear a faint melody in the middle of a thunderstorm. Another difficulty is that consciousness itself is not easy to measure. While we can observe brain states that correlate with awareness, the subjective quality of experience is something only the person can report. This makes designing experiments tricky. You cannot place consciousness in a test tube, run it under a laser, and record the results. You can only measure proxies, neural activity, molecular dynamics, behavioral responses, and then interpret what they might mean. That leaves room for debate, interpretation, and sometimes wishful thinking. Anesthetics offer one of the few reliable handles on consciousness. Administered in the right doses, they can render a person completely unaware, then allow awareness to return once the drug is removed. Some studies suggest that anesthetics interact with microtubules as well as with known neural receptors, raising the possibility that they disrupt quantum processes. However, skeptics point out that anesthetics have many known mechanisms of action at the classical level, including altering ion channels and neurotransmitter receptors. The fact that they may also interact with structural proteins does not necessarily mean that consciousness itself is quantum. Animal studies and computational models have also been used to probe the idea. Some computer simulations suggest that quantum effects in microtubules could, in principle, last longer than previously assumed. Other models argue the opposite, predicting that decoherence would wipe out quantum states almost instantly in such a noisy environment. These conflicting results highlight how much depends on assumptions built into the models. Without direct experimental confirmation, the debate remains unresolved. The broader neuroscience community remains unconvinced for a simple reason. So far, there has been no clear evidence that requires quantum mechanics to explain consciousness. Every phenomenon studied in the brain, from memory consolidation to decision-making, can be accounted for by classical neural networks. This does not prove that quantum processes are absent, but it does suggest they are not necessary to explain what we observe. Why is hard evidence so elusive? Partly because the brain is an extraordinarily difficult system to study. Unlike photons or electrons, neurons cannot be neatly isolated and controlled. They interact constantly with thousands of neighbours, and their activity is influenced by chemistry, metabolism, and environment. Even with the most advanced tools, disentangling the role of quantum effects from the overwhelming background of classical processes is daunting. Another reason is that quantum mechanics itself is subtle. The phenomena we associate with it, coherence, entanglement, tunneling, are fragile and often fleeting. Detecting them in biological tissues requires extreme precision, and even then, distinguishing genuine quantum behavior from ordinary molecular noise can be nearly impossible. Many experiments in quantum biology succeed only because the systems involved, like photosynthetic complexes, are relatively simple and optimized by nature for specific tasks. The brain, by contrast, is messy, dynamic, and filled with redundant pathways. This does not mean the search is pointless. On the contrary, even negative results teach us something. They remind us to be cautious, to avoid confusing metaphor with mechanism, and to demand solid data before revising our understanding of the mind. They also encourage innovation, pushing researchers to design new kinds of experiments and instruments that might one day probe the brain at the quantum level. For now, the balance of evidence leans towards skepticism. Consciousness does not appear to require quantum mechanics, at least not in any form we can currently measure. The tantalizing hints, microtubule vibrations, anesthetic interactions, unusual correlations, remain intriguing but inconclusive. They are sparks, not yet a fire, and yet the allure of the search persists. The possibility that quantum mechanics could play a role in awareness is too fascinating to abandon outright. It sits at the intersection of some of our deepest mysteries, inviting both curiosity and caution. Whether future experiments will reveal hidden quantum threads in the fabric of the mind, or whether they will confirm the sufficiency of classical neuroscience remains to be seen. Until then, the evidence will remain elusive, shimmering like a quantum superposition, possible but not yet observed. One of the strongest challenges to the idea that consciousness requires quantum mechanics comes from a very modern source: artificial intelligence. Over the past few decades, machines have become increasingly sophisticated in their ability to process information, recognize patterns, and even mimic human conversation. Whether or not these machines are truly conscious is hotly debated, but their existence raises an important question. If silicon-based systems can, at the very least, display intelligence without relying on quantum effects, why assume that carbon-based brains need them? Artificial intelligence is built on classical computation. At its core, a computer is nothing more than a network of switches, turning on and off in precise patterns. These switches can represent numbers, instructions, or bits of information. Layered together, they form processors that can calculate, simulate, and learn. There is no hint of superposition or entanglement in ordinary computation. Everything is deterministic and grounded in the physics of transistors. Yet from this foundation, machines have achieved feats once thought to require human-level intelligence. Consider how AI now handles language. Algorithms can generate essays, translate between dozens of languages, and even compose poetry. Other systems play strategy games like Go or chess at levels far beyond the best human players. Some can recognize faces in a crowd or detect patterns in medical scans that trained specialists might miss. These accomplishments are not signs of consciousness in themselves, but they show how far complexity can go without invoking quantum magic. The same principles of learning and adaptation that power machine intelligence are also central to the workings of biological brains. This leads to a provocative question. If a machine built from transistors can mimic thought through sheer computational power, is there really a need to imagine that neurons must be exploiting fragile quantum states to achieve awareness? The analogy is imperfect. Machines may not feel emotions, savor chocolate, or daydream about holidays, but the fact that they can replicate many aspects of intelligence without quantum mechanics weakens the case for its necessity in consciousness. Skeptics of quantum consciousness often point to this very comparison. The brain and a computer are both systems that process information. One is built of biological neurons, the other of silicon transistors. If both can, in principle, learn, adapt, and make decisions using classical physics, then perhaps the extraordinary qualities of the mind are simply what happens when information processing reaches a certain level of complexity. In this view, consciousness is not about what materials you're made from, or whether you exploit quantum coherence. It is about the patterns of organization and the dynamics of computation. Of course, this does not settle the question of whether AI is conscious. Many argue that no matter how sophisticated an algorithm becomes, it still lacks subjective experience. A machine may respond to a question about pain, but it does not actually feel it. It may recognize a sunset, but it does not marvel at the colors. This distinction between processing information and having an inner life lies at the heart of what philosophers call the hard problem of consciousness. Still, even if AI lacks true awareness, it demonstrates that much of what we associate with intelligence and cognition can be achieved without appealing to quantum physics. Some thinkers take the comparison further. If we eventually build machines that are indistinguishable from humans in behavior, language, and creativity, then at what point would we grant them the status of being conscious? If their inner workings are entirely classical, then consciousness clearly does not require quantum mechanics. It would show that awareness can emerge from complexity alone, regardless of the underlying material. That does not prove the human brain works the same way, but it strongly suggests that quantum effects are not mandatory. There are also philosophical arguments that support this line of thought. One of them is the principle of parsimony, often called Occam's razor. When two explanations exist, the simpler one that requires fewer assumptions is usually preferred. If classical neuroscience and computational models can account for consciousness, then invoking quantum mechanics may be unnecessary. Unless experiments show otherwise, adding exotic physics risks complicating the picture without offering clear advantages. Still, some remain unconvinced. They argue that while AI may mimic intelligence, it does not capture the richness of human experience. Machines can simulate conversation, but they do not feel empathy. They can analyze music, but they do not feel moved by it. These qualities, they suggest, might require something deeper than classical computation. This is where proponents of quantum consciousness see an opening. Perhaps the missing ingredient, the bridge from information processing to genuine awareness, lies in quantum processes. But even here, the comparison with AI remains instructive. If the argument is that machines cannot be conscious because they lack quantum effects, then one must explain exactly why. What is it about superposition or entanglement that would grant subjective experience? So far, no one has provided a clear mechanism. Meanwhile, computers continue to advance, growing ever more human-like in their capabilities. The more they achieve, the harder it becomes to insist that quantum mechanics is essential. The debate also touches on another important point. Consciousness may not be tied to the material at all, but to the organization of information. From this perspective, what matters is the architecture of the system, the way signals are processed, and the feedback loops that integrate information. A human brain, an animal brain, or even a sufficiently complex machine could all, in theory, support awareness if the organization is right. This is sometimes called functionalism, the idea that mental states are defined not by their physical substrate, but by their function. If functionalism is correct, then neurons are not magical, nor are transistors, nor would quantum states be. What matters is how the pieces are arranged and how they interact. In that case, consciousness is not about exploiting the strangeness of physics, but about reaching a threshold of complexity where awareness emerges. The brain may have achieved this through evolution, while AI may eventually achieve it through design. In neither case would quantum mechanics be a requirement. The debate over AI consciousness is far from settled, but it sharpens the central question. If machines built on classical principles can achieve so much, why assume the brain requires something more exotic? Until evidence shows otherwise, the burden of proof rests on those who argue that quantum effects are essential. At the very least, AI demonstrates that intelligence, problem-solving, learning, adaptation can thrive without quantum mechanics. Whether it also achieves consciousness remains an open question. But the comparison suggests a humbling possibility. Perhaps the mind is not dependent on hidden quantum processes, but is instead a natural outcome of information processing taken to its most complex form. And if that is true, then the mystery of consciousness, as daunting as it is, may one day be explained not by new physics, but by a deeper understanding of the systems we already know. Quantum computers are often hailed as the next great leap in technology, machines that will make even the fastest supercomputers look sluggish. They are not just faster calculators, they work on principles that are fundamentally different from the computers we use today. Instead of processing information in bits that are either 0 or 1, quantum computers use qubits, which can exist in superpositions of 0 and 1 at the same time. This allows them to explore many possibilities simultaneously, solving certain problems with an efficiency that classical machines cannot match. It is not surprising, then, that people have drawn parallels between quantum computers and the human mind. If thought itself feels like a mysterious dance of possibilities collapsing into decisions, could our brains be operating like quantum processors? And if we build a sufficiently advanced quantum computer, might it begin to think, reason, or even become conscious in ways that resemble us? At first glance, the comparison is compelling. Quantum computers can juggle multiple states at once, echoing the way human beings seem to consider multiple options before choosing one. They can also harness entanglement, where qubits share correlations no matter how far apart they are. This strange property has a tempting parallel in the way our thoughts often feel interconnected, as if ideas leap across the mind without a clear chain of reasoning. To those intrigued by quantum consciousness theories, quantum computing feels like a natural metaphor for the brain. Yet the differences are just as important as the similarities. For one, quantum computers are designed for specific types of problems, factoring large numbers, simulating molecules, optimizing complex systems. These are tasks where superposition and entanglement can be harnessed in structured ways. Human thought, by contrast, is fluid, adaptive, and often irrational. A quantum computer may calculate the most efficient path through a problem space, but it does not daydream, reminisce about childhood, or feel moved by a piece of music. Another limitation is that quantum computers, at least as they currently exist, are extremely fragile. Maintaining coherence in qubits requires shielding them from the environment, cooling them to near absolute zero and correcting for errors that creep in constantly. The human brain, on the other hand, thrives in a noisy, warm environment with neurons firing in an intricate ballet that is surprisingly robust. If our brains do use quantum effects, they do so in a way far more stable and adaptable than the delicate qubits in a laboratory. There is also the matter of architecture. The brain is not just a processor. It is a living system shaped by evolution, filled with feedback loops, neurotransmitters, and dynamic plasticity. Memories are not stored like files in a folder, but woven into patterns of connections that shift with every new experience. A quantum computer, no matter how sophisticated, is still a machine built for computation, not for the messy business of being alive. It may simulate certain aspects of thought, but it does not grow, learn, or adapt in the open-ended way a brain does unless carefully programmed to do so. The question of whether a quantum computer could become conscious brings us into the realm of philosophy. If consciousness arises simply from information processing, then in principle any sufficiently advanced system, classical or quantum, could achieve it. Functionalists argue that what matters is not the material substrate but the patterns of organization. In that case, a quantum computer designed with the right architecture could, at least in theory, host consciousness. But if consciousness requires something more, if it depends on the unique biological context of neurons, chemistry, and perhaps even quantum processes in microtubules, then machines, no matter how advanced, may remain sophisticated zombies, intelligent, capable, but without an inner life. The allure of quantum computers as models of the mind also stems from their novelty. Classical computers are now so familiar that comparing them to brains feels uninspiring. But quantum computers are strange, exotic, and still not fully understood by most. Their mystery makes them attractive analogies for consciousness, which is equally elusive. Saying, the brain is like a quantum computer, feels richer than saying, the brain is like a very complicated calculator, even if both are metaphors with limits. There are also practical overlaps. Quantum computers excel at simulating molecules and biological systems, which could eventually help us model neural processes in unprecedented detail. They may allow researchers to explore how complex brain chemistry gives rise to cognition, not because they are conscious themselves, but because they are powerful tools. In this way, quantum computers may help unravel consciousness without actually possessing it. It is worth remembering that history is full of comparisons between the brain and the most advanced technology of the time. In the 17th century, Descartes likened the body to a mechanical clock. In the 19th century, brains were compared to telegraph systems. In the 20th century, they were compared to classical computers. Now, in the 21st, quantum computers have taken their place as the metaphor of choice. Each comparison reveals something useful but eventually shows its limits. Brains are not clocks, telegraphs, or computers. They are living, evolving systems, and their mysteries extend beyond any single analogy. So could a quantum computer think like us? It depends on what thinking means. If it means solving complex problems, making decisions, or even learning patterns from experience, then yes, quantum computers could eventually rival or surpass us in certain domains. But if thinking includes subjective experience, the feeling of being, the richness of perception, the inner narrative that colours every moment, then the answer is far less clear. So far, nothing about quantum computation suggests that awareness would automatically emerge from qubits, any more than it does from transistors. The comparison is compelling because it highlights the strange and powerful potential of both brains and quantum mechanics, but it is incomplete because it glosses over the biology, the history, and the lived quality of consciousness. Quantum computers may one day revolutionize science and technology, but whether they will ever sit quietly and wonder about their own existence remains an open question. Until then, the human mind remains unique, a blend of matter and mystery, capable of contemplating itself and the universe, including the machines it builds to imitate its own brilliance. There is something undeniably seductive about linking consciousness to quantum physics. Even if the scientific evidence is uncertain, the very sound of the phrase quantum mind has an aura of mystery. It suggests hidden depths, secret connections, and a universe that is more than it seems. For many, this appeal goes beyond science and enters the territory of meaning, unity, and wonder. It is less about equations and experiments and more about how the idea makes people feel, part of something vast and interconnected. One reason people love the idea is that it bridges two great mysteries. On one side is consciousness, the deeply personal experience of being alive. On the other is quantum physics, the strange and counterintuitive rules that govern the tiniest scales of reality. Each alone is puzzling enough, but put them together and it feels as though you're holding the keys to a hidden realm. The temptation is obvious. If the mind is quantum, then perhaps our awareness is connected to the very foundations of the universe. That is a thought capable of stirring both awe and comfort. The language of quantum physics also lends itself well to metaphor. Words like superposition, entanglement, and uncertainty are rich with symbolic meaning. It is no wonder that these terms have been adopted far beyond physics, appearing in books about spirituality, self-help, and even wellness. The notion of being entangled with another person sounds romantic, even if in physics it refers to correlations between particles. Likewise, the idea of superposition can be stretched into a metaphor for holding multiple possibilities in life until a choice is made. And uncertainty, rather than being a mathematical principle, becomes a reflection of the open-ended nature of existence. Here is where a little gentle humour is useful. Quantum is sometimes used as a cosmic spice. Sprinkle it on any mystery, and it suddenly sounds profound. From quantum healing to quantum success coaching, the word has become a kind of shorthand for depth, even when no actual physics is involved. Of course, this does not mean the ideas being sold are scientifically accurate, but it does show how powerful the allure of quantum imagery has become. When you attach the word quantum to anything, it instantly gains a sheen of mystery and authority. Part of this appeal lies in the way quantum physics challenges our everyday intuitions. We are used to objects being solid, definite, and predictable. Quantum mechanics overturns that with particles that blur between states, influences that cross space instantly, and outcomes that only emerge when measured. It makes the universe feel alive with strangeness. If the mind is somehow tied into this hidden order, then consciousness itself seems less like a local accident of biology and more like a window into the deep structure of reality. That can be profoundly reassuring to people who worry that consciousness is otherwise just neurons firing in the dark. There is also a psychological reason why the idea resonates. Humans crave connection. We like to believe we're linked not only to each other, but also to the universe itself. Quantum mechanics, with its entanglement and uncertainty, provides a framework that makes this longing sound scientific. It whispers of unity, of being part of a web that extends far beyond the boundaries of the self. Even if the physics does not literally say this, the metaphors are irresistible. Cultural history adds to the mix. Throughout the 20th century, as quantum mechanics entered the public imagination, it collided with philosophical traditions from the East, such as Buddhism and Taoism. Thinkers noticed similarities between ancient ideas of interconnectedness and the new physics of entanglement. Books began to blend the two, suggesting that quantum mechanics confirmed what sages had intuited for centuries. While physicists often objected that the parallels were more poetic than precise, the cultural fusion stuck. To this day, people still invoke quantum physics in spiritual contexts as if it were a bridge between science and mysticism. Even within the scientific community, the strangeness of quantum theory has left room for wonder. Famous physicists like Richard Feynman admitted that no one truly understands quantum mechanics at an intuitive level. The equations work, the predictions are flawless, but the mental picture is slippery. This ambiguity leaves a space where philosophy and imagination rush in. If even the experts admit the theory is puzzling, then it feels natural for non-scientists to see it as an open canvas for their own interpretations. The mystical appeal of quantum consciousness is not only about unity with the cosmos, but also about elevating the human mind. If our awareness is tied to the fundamental fabric of reality, then consciousness is not an accident of evolution, but something woven into existence itself. This grants the mind a kind of cosmic dignity. It reassures us that we are not just biological machines, but participants in the unfolding of the universe. For many, that idea is worth holding on to, even if the evidence is lacking. It is important, however, to balance the wonder with caution. The danger of leaning too heavily on quantum mysticism is that it can turn vague. If every unexplained phenomenon is attributed to quantum effects, the term risks losing meaning. Physics becomes a placeholder for mystery rather than a tool for understanding. Scientists remind us that genuine quantum mechanics is precise, mathematical, and testable, even if its implications are strange. Consciousness may indeed connect to quantum processes, but that claim must stand on evidence, not just on poetic resonance. Still, the fact that people are drawn to the idea speaks to something valuable. It shows a deep desire to find unity between inner and outer worlds, between subjective experience and the fabric of reality. Even if the theory turns out to be wrong, the fascination reveals how humans seek meaning in mystery. Quantum physics has become a mirror in which we see not only particles and probabilities, but also our longing for connection, depth, and wonder. And perhaps that is the most enduring lesson of the mystical appeal. Quantum mechanics may not provide proof that consciousness shapes reality, but it does remind us that reality is far stranger than it appears. If the smallest building blocks of nature behave in ways that defy common sense, then it is no surprise that consciousness too feels elusive. Linking the two may be more metaphor than mechanism, but metaphors have power. They shape the way we think, the way we imagine, and the way we feel about our place in the cosmos. In the end, the mystical appeal of quantum consciousness is not just about science, it is about the human need for wonder. It shows that even in an age of advanced technology and rigorous experimentation, we still yearn for the mysteries that science alone cannot explain away. Whether or not quantum physics ever turns out to hold the key to the mind, it has already given us something profound, a reminder that the universe is richer, stranger, and more interconnected than we once believed. Quantum consciousness has an undeniable charm, but step into a neuroscience lab or a physics department, and you will find that many scientists greet the idea with raised eyebrows. For them, the proposal that awareness emerges from quantum mechanics is not only unproven, but also plagued with problems of vagueness, lack of evidence, and a worrying inability to make testable predictions. In short, it looks less like a scientific theory and more like a philosophical story dressed in the language of physics. One of the strongest objections is on falsifiability. In science, a theory is considered valuable only if it can, in principle, be proven wrong. Einstein's theory of relativity, for instance, predicted the bending of starlight by gravity. If astronomers had not observed that bending during a solar eclipse, the theory would have been dealt a serious blow. Quantum consciousness theories, by contrast, often seem slippery. They claim that awareness arises from quantum effects in the brain, but rarely state what evidence would count as disproof. If you scan the brain and find no quantum activity, proponents might say the effects are hidden. If you discover complex neural activity explained classically, they might argue the quantum processes are still there, just deeper. Without clear criteria for falsification, critics worry that the idea floats forever, immune to evidence. Closely tied to this is vagueness. Traditional physics theories specify mathematical relationships and make numerical predictions. Quantum consciousness proposals often deal in broad analogies. Words like superposition, coherence, and entanglement are borrowed from physics and mapped onto mental life, but without precise definitions. What does it mean, exactly, for a thought to be in a superposition? How would one measure entanglement between mental states? Without clarity, the terms risk becoming metaphors rather than mechanisms. Scientists are wary of metaphors that masquerade as explanations. Then there is the issue of predictive power. Good theories not only explain known facts, but also predict new ones. The double-slit experiment, for instance, predicted interference patterns that had not yet been seen. DNA's structure predicted mechanisms of replication. But quantum consciousness has not generated similarly concrete predictions. It explains consciousness in retrospect, but struggles to forecast anything specific. This leaves it vulnerable to the criticism that it is an after-the-fact story rather than a forward-looking scientific theory. Another major reason for skepticism is the lack of empirical evidence. Despite decades of neuroscience research, no experiment has conclusively demonstrated that quantum effects are required for consciousness. Brain imaging reveals patterns of activation that correlate with perception, thought, and memory. But none of these findings necessitate quantum mechanics. Neurons communicate through well-understood electrochemical processes, and the dynamics of networks can be modelled without invoking quantum states. Theories like OR, which suggest that microtubules host quantum coherence, remain unproven and controversial. While some laboratory results hint at unusual vibrations in microtubules, these findings have not been replicated widely or tied directly to awareness. For skeptics, the burden of proof lies firmly with proponents, and so far the evidence falls short. Physicists also highlight the practical problem of decoherence. Quantum states are notoriously fragile, collapsing rapidly when disturbed by interactions with the environment. That is why quantum computers require extreme cooling and isolation to function. The brain, in contrast, is warm, wet, and noisy. Neurons fire constantly, molecules jostle, and ions rush across membranes. Expecting delicate quantum states to survive in such conditions seems implausible. To many physicists, the notion of robust quantum computation happening inside neurons sounds like trying to build a snowflake in the middle of a bonfire. Skeptics further argue that appealing to quantum mechanics risks becoming a kind of intellectual shortcut. History is full of mysteries that once seemed impenetrable, but were eventually explained without resorting to exotic new laws. Lightning was once considered divine wrath, until electricity was understood. Disease was attributed to curses until germs were discovered. Consciousness, skeptics say, may follow the same pattern. It feels extraordinary because it is complex, not because it demands new physics. Invoking quantum mechanics prematurely may distract from the slow, methodical work of neuroscience that is already making progress. There is also a sociological element. Scientists are wary of how quantum has been misused in popular culture. From quantum healing to quantum astrology, the word has been stretched to cover ideas with little or no scientific grounding. When proponents of quantum consciousness make vague claims, it risks blurring the line between rigorous physics and pseudoscience. Many researchers feel protective of quantum mechanics, wanting to prevent its misuse as a buzzword detached from its mathematical roots. The worry is that quantum consciousness, even if proposed sincerely, may unintentionally encourage the same misunderstandings. None of this means that skeptics dismiss the mystery of consciousness itself. On the contrary, many neuroscientists freely admit that the hard problem remains unsolved. They acknowledge that subjective experience is difficult to explain in purely physical terms, but they caution against assuming that difficulty automatically points to quantum solutions. Mysteries are not evidence for exotic answers, they are invitations to keep searching carefully. The history of science shows that patient investigation often yields explanations within existing frameworks, even when the problem initially seemed insurmountable. Another point raised by skeptics is that even if quantum processes occur in the brain, that does not prove they are necessary for consciousness. Biology is full of phenomena where quantum mechanics plays a subtle role: photosynthesis, bird navigation, enzyme reactions. But these processes are not conscious. They are biochemical tricks that evolution has harnessed for efficiency. If the brain uses quantum effects in some molecular processes, it does not automatically follow that awareness depends on them. Correlation is not causation, and the leap from quantum biology to quantum mind is a big one. Some critics also note that the appeal of quantum consciousness may stem from a kind of psychological comfort. Linking the mind to the deepest level of reality elevates human experience, making it feel cosmic rather than biological. It resists reductionism by offering a grander story. While this is understandable, science aims to resist comforting narratives unless they are backed by evidence. To scientists, the human tendency to seek meaning in mystery is not proof of quantum consciousness, but a reminder to stay vigilant against wishful thinking. For these reasons, many scientists view quantum consciousness as an interesting speculation, but not yet a scientific theory. It lacks clarity, testability, and evidence. It risks confusing metaphor with mechanism and comfort with explanation. Consciousness may indeed turn out to involve surprises we cannot yet imagine, but skeptics argue that quantum mechanics should not be invoked until experiments demand it. And there is still plenty of room for wonder without it. The brain, with its billions of neurons and trillions of connections, is one of the most complex systems in the known universe. Its ability to generate thought, memory, imagination, and awareness is extraordinary even without appealing to new physics. Skeptics remind us that we should not underestimate complexity. Sometimes the most astonishing phenomena emerge not from exotic principles, but from the sheer richness of ordinary processes, repeated and refined over billions of years of evolution. In the end, the skeptical case does not close the door on quantum consciousness. It simply asks for the same standards applied to any scientific idea: clear definitions, testable predictions, and solid evidence. Until those are provided, the theory remains more philosophy than physics. That does not make it worthless. Philosophy has always played a role in guiding science, but it does mean the burden of proof remains high. For now, consciousness can still be explored fruitfully with the tools of neuroscience, psychology, and classical physics, leaving quantum mechanics to rest in its rightful place until the evidence calls it forward. Between the bold claims of quantum enthusiasts and the firm skepticism of neuroscientists lies a quieter and perhaps more reasonable position. This middle ground does not insist that consciousness is entirely quantum, nor does it dismiss the possibility outright. Instead, it allows that while the brain's complexity is likely enough to generate awareness through classical processes, quantum mechanics may still play a subtle role, perhaps influencing thought in ways we do not yet fully understand. It is a view that makes room for wonder without requiring leaps beyond evidence. The first step in this balanced approach is acknowledging that consciousness almost certainly arises from the brain's physical activity. Neuroscience has shown again and again that damage to specific regions alters awareness, that drugs and chemicals can switch it on and off, and that patterns of neural activity correlate with states of mind. Consciousness is not floating above the brain like a ghost. It is intimately tied to neural processes. From this perspective, emergence provides a powerful explanation. Just as the collective behavior of countless water molecules produces the quality of wetness, the coordinated activity of billions of neurons may produce the phenomenon of consciousness. At the same time, it's fair to note that the brain is not just another complex system. Its sensitivity, adaptability, and creativity make it stand apart from many other forms of emergent behavior. Ant colonies are complex, yet they do not ponder the meaning of existence. Weather systems are chaotic, but they do not write poetry. Something about the brain's organization gives rise to the rich inner life of awareness, and while classical physics may be sufficient, it is not unreasonable to wonder if quantum effects add nuance to the story. Quantum mechanics, after all, is not confined to the laboratory. It shows up in surprising corners of biology, from the efficiency of photosynthesis to the way some birds navigate. These discoveries have taught scientists that life can and does harness quantum effects when it's advantageous. If plants and birds can exploit coherence and entanglement, then it is not unthinkable that brains might also do so, even if only in small supporting ways. The middle ground does not claim that quantum physics explains consciousness outright, but it suggests the possibility that subtle quantum contributions may enrich or influence processes that are largely classical. Take the idea of decision-making. Classical neuroscience can describe how neurons integrate inputs and produce outputs, yet the sense of freedom in choosing between options feels less mechanical. Could quantum indeterminacy at microscopic scales introduce a degree of unpredictability into neural firing patterns? Perhaps these small fluctuations do not create consciousness, but contribute to its flavour, adding an element of novelty to otherwise deterministic processes. The brain could remain an emergent classical system, but with quantum physics adding a faint shimmer of unpredictability, much like a spice enhancing a recipe without changing its essential nature. Similarly, memory storage and retrieval might be influenced by subtle quantum effects in molecular structures. Some researchers have speculated that quantum coherence within microtubules or proteins could contribute to the timing and coordination of neural signals. Even if these processes are not the foundation of consciousness, they might shape how efficiently information flows. In this way, quantum mechanics could play a supporting role, not the starring one. The middle ground also respects the limitations of evidence. It accepts that no experiment has yet proven the necessity of quantum processes in the brain, and it acknowledges the force of skepticism regarding decoherence in warm, wet environments. But it balances that with openness to discovery. History is full of moments when nature surprised us. For centuries, no one suspected that birds could sense magnetic fields, or that photosynthetic complexes could maintain coherence at room temperature. The lesson is humility. Sometimes biology finds ways of exploiting physics that we would not have predicted. What makes this position appealing is its moderation. It avoids the overreach of claiming that quantum physics is the secret key to consciousness, while also avoiding the rigidity of declaring it impossible. Instead, it emphasizes that the story of the mind is likely a blend of classical complexity and perhaps, in certain niches, subtle quantum effects. This balanced speculation does not diminish the wonder of either science. In fact, it highlights the beauty of emergence, the idea that extraordinary phenomena can arise from ordinary ingredients, sometimes enhanced by delicate influences that push the boundaries of possibility. There is also a poetic resonance in this view. To think of consciousness as emergent aligns it with countless other wonders of nature: the fractal growth of snowflakes, the murmuration of starlings, the spirals of galaxies. At the same time, to allow for a touch of quantum possibility reminds us that life and awareness may be even stranger than we currently grasp. It is a vision that honours both the solidity of evidence and the allure of mystery. Critically, the middle ground also reframes the debate. It suggests that asking, "Is consciousness quantum or not?" may be too blunt. The better question might be, to what extent and in what ways could quantum mechanics contribute to the phenomena we call awareness? Consciousness may be primarily a classical emergent property of neural networks, with quantum effects acting as whispers rather than shouts. They may not be necessary for the existence of mind, but they could still influence its texture, its unpredictability, or its efficiency. This approach also has practical advantages. Instead of demanding a grand unifying theory of quantum mind, researchers can design experiments to look for specific quantum contributions in neural processes. They can investigate whether microtubules exhibit coherence, whether entanglement might play a role in signal timing, or whether quantum tunneling occurs in synapses. The middle ground encourages inquiry without exaggeration, exploration without dogma. It is worth emphasizing that even if the brain is entirely classical, the mystery of consciousness remains profound. Emergent behavior at the scale of billions of neurons is astonishing in its own right. Awareness could be extraordinary without quantum mechanics, just as music is extraordinary without needing new laws of physics to explain it. But if quantum mechanics does play a supporting role, then consciousness becomes an even richer story, woven from both the complexity of biology and the strangeness of fundamental physics. In the end, the middle ground is less about answering the question once and for all, and more about keeping the question alive in a responsible way. It is an acknowledgement that we do not yet know the full story of the mind, but that speculation should be tempered with evidence and humility. It leaves space for curiosity, while respecting the boundaries of what science has shown so far. Perhaps the best way to put it is this: consciousness may not need quantum mechanics, but it might not be entirely free of it either. The brain is a masterpiece of emergent complexity, and within its billions of cells there may also be delicate threads of quantum behaviour, subtle but real. Whether those threads prove to be central or incidental, they remind us that the search for understanding is not about closing doors, but about leaving them ajar, allowing wonder and discovery to enter in equal measure. Quantum consciousness may be on shaky ground scientifically, but culturally it has enjoyed a long and surprisingly influential life. If you step outside the walls of laboratories and universities, you find the idea thriving in books, films, spiritual teachings, and even the self-help aisle. While physicists debate wave functions and neuroscientists map synapses, the broader public often embraces the notion that consciousness is deeply tied to quantum mysteries, and it is not hard to see why. The allure begins with storytelling. Films in particular have leaned heavily on quantum themes to explore questions of mind, reality, and perception. Think of movies where alternate realities branch with every choice, or where observation itself changes what is real. Science fiction has long been fascinated with the idea that quantum physics blurs the boundary between mind and matter. Even when the details of the science are stretched or outright invented, the metaphors resonate. A quantum multiverse is a perfect stage for exploring the consequences of free will. A collapsing wave function becomes a plot device to suggest that human choice shapes destiny. Audiences do not necessarily demand precision. They crave wonder, and quantum consciousness provides it in spades. Books have also played a central role in popularizing the idea. From thoughtful philosophical explorations to more speculative works, the shelves are filled with titles that link the quantum world with the mysteries of the mind. Some are written by scientists who sincerely wrestle with the puzzle, blending rigorous explanation with cautious speculation. Others come from authors outside the scientific mainstream, who see in quantum physics a license to imagine profound connections. For readers, these works often provide a satisfying bridge between science and meaning. The technical details of quantum mechanics may be impenetrable, but the broad strokes, uncertainty, superposition, entanglement, become symbols that people can carry into their own reflections about life and selfhood. Spiritual movements too have eagerly embraced quantum consciousness. For centuries, traditions like Buddhism, Taoism, and Vedanta have emphasized interconnectedness and the illusory nature of separation. Quantum physics, with its counterintuitive refusal to let particles remain neatly distinct, seems to echo these teachings. Entanglement is recast as spiritual unity. Superposition becomes a metaphor for the boundless potential of the soul. The uncertainty principle resonates with teachings about embracing the unknown. Even if the connections are more poetic than literal, they offer a language in which science and spirituality seem to converse. For many people, that blending feels deeply satisfying, suggesting that modern physics is finally catching up to ancient wisdom. The self-help world has taken this one step further. In this realm, quantum mechanics is often less a science than a brand. It is used to lend authority to claims about the power of thought, intention, and positive energy. The word quantum has become a kind of intellectual seasoning. Sprinkle it onto healing, meditation, or success coaching, and it instantly sounds more profound. You can find workshops on quantum healing, seminars on quantum success, and books promising quantum leaps in personal growth. Rarely do these ventures involve actual equations or experiments. Instead, quantum serves as shorthand for depth, mystery, and transformation. Why does the idea thrive so powerfully outside academia? One reason is accessibility. The real details of quantum mechanics are famously difficult, even for experts. As Richard Feynman once quipped, "If you think you understand quantum mechanics, you don't." That ambiguity creates fertile ground for imagination. If even the physicists admit they cannot fully picture what is happening, then why shouldn't philosophers, spiritual teachers, and storytellers offer their own interpretations? In the absence of a single, intuitively clear explanation, the public feels free to adopt the metaphors that resonate most with them. Another reason is the hunger for meaning. Science has done an extraordinary job explaining how things work, but it often stops short of explaining why they matter. Consciousness, in particular, feels too intimate and too important to be reduced to electrochemical signals. People want to believe that their awareness connects them to the universe in a fundamental way. Quantum physics, with its aura of mystery, provides a way to satisfy that longing without abandoning science entirely. It suggests that the deepest truths of reality and the deepest truths of the mind are not separate but entwined. Culturally, the idea also thrives because it aligns with broader themes of unity and connection. In an age where many feel isolated or fragmented, the promise of entanglement, that we are connected at the most fundamental levels, is emotionally powerful. Even if the scientific details are fuzzy, the metaphor speaks directly to human experience. We feel bound to others, influenced by unseen forces, and capable of shaping our own realities through choices and awareness. Quantum consciousness wraps these intuitions in the authority of physics. It also helps that the phrase quantum consciousness simply sounds good. It carries an air of sophistication and mystery, evoking both cutting-edge science and timeless philosophy. It is short, memorable, and versatile enough to be used in contexts ranging from film scripts to meditation retreats. In the marketplace of ideas, catchiness matters, and this phrase has a kind of built-in magnetism. Of course, academics are quick to point out the dangers of this cultural embrace. When quantum concepts are stretched too far, they can lose their original meaning. Entanglement in physics has precise mathematical rules, while entanglement in a novel might mean a soulful bond between characters. These uses are not equivalent, and conflating them can muddy understanding. But from a cultural perspective, accuracy is often less important than resonance. People are not turning to self-help books or movies for physics lessons. They are looking for metaphors that make sense of their experiences, and quantum language provides that. Interestingly, this cultural enthusiasm can sometimes circle back and inspire genuine scientific inquiry. Public fascination with quantum consciousness keeps the idea alive, funding conferences, sparking debates, and encouraging researchers to think creatively. Even when scientists dismiss the wilder claims, the cultural momentum ensures the topic is not forgotten. It demonstrates how science and culture feed each other, with imagination pushing the boundaries of what we dare to ask, and evidence grounding us in what we can confirm. The persistence of quantum consciousness in culture may say more about us than about physics. It reflects our longing to see ourselves as more than biological machines, our desire for mystery in a world that often feels over-explained, and our hope that science and spirituality are not enemies but partners. Whether or not quantum mechanics has anything to do with awareness, the cultural story is here to stay. And perhaps that is its own kind of truth. Even if the equations of quantum physics never explain why the mind feels the way it does, the metaphors we draw from it can shape how we think, how we tell stories, and how we understand our place in the cosmos. Quantum consciousness, in this sense, is less a scientific theory than a cultural myth. Not myth in the sense of falsehood, but in the sense of a narrative that captures human imagination and expresses deep hopes. It thrives outside academia because it speaks to something science alone cannot satisfy: the yearning to feel connected to a universe that is as mysterious within as it is without. the debate over quantum consciousness is unlikely to fade anytime soon. If anything, it may intensify as both neuroscience and physics continue to advance, offering sharper tools and deeper insights into the mysteries of the mind. At the heart of the question is whether consciousness can be explained entirely through classical biology, or whether the strange rules of quantum mechanics must be invoked to fill in the gaps. The tools we're developing in the 21st century will not only help refine this debate, but may also uncover entirely new puzzles that shift the conversation once again. On the neuroscience side, the progress has been extraordinary. Imaging technologies have grown far more precise than the crude scans of the late 20th century. Techniques like functional MRI now allow researchers to track blood flow changes that reflect neural activity across the entire brain in real time. Advances in magnetoencephalography and optogenetics give us even finer windows into the timing and coordination of neurons. Brain-computer interfaces are beginning to translate neural signals directly into external actions, revealing the logic of circuits once hidden in mystery. Each improvement brings us close to mapping the neural correlates of consciousness with ever greater detail. Yet these advances also remind us of how vast the challenge is. A brain contains 86 billion neurons, each connected to thousands of others. Charting the full network of these connections, sometimes called the connectome, is a task so enormous that it may take decades to complete. Even then, the leap from mapping circuits to explaining subjective experience is daunting. Still, every step in this direction strengthens the classical case. If patterns of activity can account for memory, perception, and awareness, then quantum mechanics may not be required. The better we can measure the brain, the harder it becomes for untested speculations to survive without evidence. At the same time, quantum experiments are advancing just as quickly. Where once superposition and entanglement were fragile curiosities, today they are the basis of working technologies. Quantum computers are beginning to solve problems beyond the reach of classical machines. Quantum sensors are detecting tiny changes in magnetic and gravitational fields. Researchers are learning to maintain coherence in increasingly complex systems, extending the lifetimes of quantum states even in noisy environments. This matters because it undercuts one of the strongest criticisms of quantum consciousness, that quantum effects cannot survive in warm, wet brains. If physics can learn to preserve coherence in messy systems, perhaps biology has found ways to do it too. Future experiments may probe directly whether quantum effects play roles in neural processes. For example, researchers could test whether microtubules within neurons support coherent vibrations, as some have suggested, or whether synapses involve quantum tunneling in ways that shape signal transmission. Advances in spectroscopy and nanoscale imaging might make such measurements possible. If subtle quantum signatures were detected in living brains, it would not prove that consciousness is quantum, but it would show that the building blocks of neurons are stranger than we thought. Another frontier is the interface between neuroscience and artificial intelligence. As AI systems grow more sophisticated, they provide models for how intelligence can arise from purely classical processes. If machines one day convincingly simulate human-level cognition and creativity without quantum tricks, the argument that consciousness requires quantum mechanics will weaken. But if, on the other hand, machines plateau, able to simulate intelligence but never achieving anything like genuine awareness, then the case for something missing, perhaps even something quantum, will strengthen. The trajectory of AI may therefore become an indirect test of quantum consciousness theories. It is also worth remembering that the question may evolve rather than resolve. History shows that scientific debates often lead not to simple answers, but to deeper mysteries. In the 19th century, physicists believed they understood light, only to discover its dual wave-particle nature. In the early 20th century, chemists thought atoms were the smallest units of matter, only to learn about protons, neutrons, and quarks. It is possible that as we probe consciousness with better tools, we may find phenomena that do not fit neatly into classical or quantum categories. Entirely new frameworks may be required, extending physics in ways we cannot yet imagine. For the public, the future of the debate will likely remain as much cultural as scientific. Quantum consciousness will continue to thrive in books, films, and spiritual teachings because it speaks to a deep human desire for meaning and connection. Even if neuroscientists eventually demonstrate that consciousness is fully explainable through classical processes, many will still find the quantum narrative compelling, if only as a metaphor. Conversely, if evidence emerges that quantum effects are genuinely involved, the cultural resonance will only deepen, affirming long-held intuitions about unity and mystery. In the laboratory, though, the future is about evidence. Neuroscientists will push for more detailed maps of the brain, charting its circuits with the precision of cartographers mapping a new continent. Physicists will refine their experiments, probing ever larger and more complex systems for quantum signatures. Between them lies the possibility of convergence, the day when tools are sensitive enough to say definitively whether the brain harbours quantum effects or not. Until then, the debate remains open, a superposition of possibility waiting for its measurement. Perhaps the most realistic outlook is that the coming decades will provide clarity at the edges while leaving the core mystery intact. We may rule out certain quantum theories of consciousness, while leaving others plausible. We may discover subtle quantum influences in biology without proving they are necessary for awareness. We may learn that the brain is even more complex than imagined, its emergent properties dazzling enough without requiring new physics. Or we may stumble upon phenomena that challenge our categories entirely. The future of the debate, then, is not about reaching a final answer once and for all, but about refining the questions. What exactly do we mean by consciousness? What kinds of processes are sufficient to generate it? How does subjective experience arise from physical systems, and can we ever fully capture it with objective measurement? These questions will persist regardless of whether quantum mechanics is part of the story. What seems certain is that the debate will remain lively, driven by advances in neuroscience, quantum technology, and philosophy alike. Each discovery will be another piece of the puzzle, even if the full picture is never completed. Consciousness may turn out to be quantum, classical, or something else entirely, but the journey of exploring it will continue to illuminate both the universe and ourselves. And in that journey, the balance of curiosity and humility may prove to be the most important guide of all. Consciousness, whether it turns out to be woven from the threads of quantum mechanics or entirely explainable by classical biology, remains one of the most astonishing facts of existence. The simple reality that you can hear words, imagine their meaning and reflect upon them is extraordinary. In a universe that is mostly dark matter, empty space and lifeless rocks, here is a pocket of awareness able to contemplate itself and everything around it. Even if science one day explains the mechanisms down to the last detail, the fact that experience exists at all will always carry a certain wonder. There is something beautiful about the idea that not everything is settled. Science excels at answering questions, but some mysteries linger, reminding us that the story is still unfolding. Consciousness is one of those lingering puzzles, and perhaps it always will be. Whether the mind relies on quantum effects, or emerges purely from the tangled webs of neurons, the ability to question and to wonder is itself a profound gift. It is a reminder that knowledge and mystery are not enemies but companions, each giving the other meaning. Part of the magic of consciousness is its intimacy. You never step outside of it. You live within it every moment, and yet, despite being the most immediate aspect of existence, it is also the hardest to explain. Science can describe how galaxies form, how atoms bond, and how black holes warp space-time. But when it comes to the feeling of being, the redness of a sunset, the taste of chocolate, the sound of laughter, explanations quickly grow thin. This paradox that the most familiar thing is also the most mysterious is enough to make one pause in quiet reflection. Speculations about quantum consciousness add another layer to this mystery. Even if the evidence remains elusive, the very idea that awareness could be linked to the fundamental rules of reality has a kind of poetry. It ties the inner world of thought to the outer world of particles, hinting at unity across scales. And even if the connection proves metaphorical rather than literal, it still enriches the way we think about our place in the cosmos. Sometimes metaphors guide us just as powerfully as equations. But there is also something equally poetic about the skeptical view. To imagine consciousness as the product of emergent complexity, billions of neurons firing in intricate harmony, is no less awe-inspiring. Out of the same atoms that form stars and soil, evolution has shaped a system capable of love, creativity, and curiosity. That such richness could arise without any exotic new physics is a marvel in itself. In this light, awareness is not a cosmic anomaly, but a natural flowering of matter, a testament to the power of complexity. Perhaps the deepest beauty lies in holding both possibilities at once. Consciousness may be classical, quantum, or something entirely beyond our current imagination. The uncertainty does not diminish it. In fact, the uncertainty may be part of what makes it precious. Living with mystery encourages humility. It reminds us that our knowledge, however advanced, is still just a small island in an ocean of the unknown. That ocean is not frightening but expansive, inviting us to continue exploring. There's also comfort in recognizing that not knowing is part of the human condition. For centuries, people have asked where thoughts come from, what dreams mean, and what it is to be aware. The answers have shifted with culture, philosophy, and science, but the questions themselves endure. To rest in the mystery of consciousness is to join a long line of thinkers, poets, and wanderers who found meaning not only in certainty, but also in wonder. One might even say that the mystery is part of what makes consciousness meaningful. If every detail were laid bare, if awareness were reduced to equations and circuits without remainder, some of the magic would vanish. The ability to marvel, to feel that there is more than can be captured in words, is part of what makes being alive so rich. A life with no mysteries would be a life with less imagination. Quantum consciousness, whether true or not, symbolizes this interplay between knowledge and wonder. It suggests that the mind may touch the very foundations of reality, or at the very least, that reality is strange enough to invite such speculation. Even if the theory fades, the longing it expresses, to feel connected, to glimpse hidden depths, will remain. That longing is as much a part of consciousness as neurons and synapses. When all is said and done, perhaps the most profound fact is not whether consciousness is quantum, but that it exists at all. Out of a silent universe came awareness capable of asking these questions, of telling stories, of seeking meaning. Whether the explanation is rooted in entangled qubits or in emergent neural networks, it does not lessen the wonder. Awareness is its own miracle, one that requires no adornment to be astonishing. So it may be best to rest gently in the mystery, to let the questions linger without rushing to closure, to savor the fact that consciousness, whether classical or quantum, is the lens through which all of reality is known. In the end, it may not matter whether the brain is a quantum computer or a classical machine of breathtaking complexity. What matters is that it is capable of wonder, of curiosity, and of love. And in that quiet recognition one finds peace. The mystery remains, but so too does the beauty of being alive to notice it. Consciousness and quantum mechanics, two of the deepest mysteries in science, make a tempting pair. One is the intimate mystery of being aware, the other the strange framework that governs the smallest particles in existence. Put them together, and you have a theory that is both fascinating and flawed, inviting curiosity while also requiring careful skepticism. The journey through these ideas shows why the notion of quantum consciousness refuses to disappear. It connects our inner lives to the foundations of the universe, offering a vision of awareness as something more than neural chemistry, perhaps even something woven into reality itself. It satisfies a longing for connection, unity, and depth. It is no wonder that philosophers, spiritual teachers, and storytellers have embraced it so eagerly. The metaphors are rich, the imagery compelling, and the promise profound. At the same time, science demands more than a lure. The skeptics are right to point out that so far there is little hard evidence that quantum mechanics plays a role in consciousness. The brain is a noisy, warm environment, hardly the kind of place where fragile quantum states are expected to thrive. Neuroscience continues to explain more and more of the mind's workings in classical terms: neurons, synapses, and networks of activity that correlate tightly with mental states. The progress is real, and it shows that consciousness, however mysterious, may not need exotic physics to exist. This balance between fascination and caution is important. On one side lies the danger of exaggeration, of turning quantum consciousness into a catch-all explanation, more poetic than scientific. On the other lies the risk of dismissal, of closing off possibilities simply because they sound strange. The middle ground is where curiosity lives, open to wonder, but careful not to confuse speculation with proof. It is also where history teaches us to stand. Time and again, science has revealed truths that were stranger than expected. The Earth orbits the Sun. Time is relative. Particles can behave like waves. Life itself may harness quantum tricks in photosynthesis and navigation. The world has a way of surprising us. At the same time, not every mystery requires new physics. Lightning turned out to be electricity, not divine anger. Disease was caused by germs, not curses. Sometimes the most astonishing discoveries emerge from the ordinary, studied carefully and deeply. So where does that leave consciousness? It leaves it where it has always been, an open question perched at the edge of knowledge. Quantum mechanics may one day prove to play a role, or it may turn out to be irrelevant. Consciousness may be fully explained by emergent complexity in the brain, or it may require frameworks we have not yet imagined. Both possibilities remain on the table. What is clear is that the search is far from over, and that the act of searching enriches science and philosophy alike. There is something hopeful in this uncertainty. The mystery of consciousness is not a wall, but a horizon. Each new advance in neuroscience, each new experiment in quantum physics, pushes that horizon a little further. The more we learn, the more we realize how much remains unknown. That is not failure. It is the essence of exploration. Mystery is not an obstacle to knowledge, but an invitation to keep asking questions. Perhaps that is the lesson to carry forward, that consciousness, whether quantum or not, is wondrous. It is the lens through which all of reality is known, the stage on which every experience unfolds. To sit quietly and reflect on the fact that awareness exists at all is to feel something both humbling and uplifting. It reminds us that being alive is not just a biological fact, but also a source of wonder, so we can rest gently in the balance. Quantum consciousness may be fascinating, but it is not proven. Neuroscience may be powerful, but it has not yet solved the riddle. Both paths remain open, each offering insights and each demanding humility. In the meantime, we can appreciate the beauty of not knowing everything. We can allow the mystery itself to be a source of peace, a reminder that life is richer when there are still questions to ask. As the day ends and the mind drifts towards sleep, perhaps the most calming thought of all is this: whether consciousness is rooted in neurons, quantum states, or something entirely beyond our current understanding, the fact of awareness remains a quiet miracle. It does not need to be solved to be cherished. The mystery is part of its beauty, and in that beauty there is hope. Hope that the search will continue, gently, thoughtfully, and with the wonder it deserves,